Hello, Gabriela, can you hear me? Everybody there, can you hear us?
Hi, I can hear you, yes. Can you hear me?
Yes, clearly.
Okay.
We're just waiting for some more people to come after the lunch.
That's okay. I just was not sure if my Zoom works properly.
Excuse me, okay. Hello. Okay, well, welcome back everybody to our workshop. We'll restarting now with the next talk by Dr. Gabriela Pastor regarding the title Luminosity Measurements in LHC Experiments. So please go ahead, Gabriela. You have 50 minutes.
Can you see my screen?
Yes, it's not full screen, but okay. Yeah.
It should be soon.
Yeah. Now it's okay. Perfect.
Okay, so I was told I have a bit more time, but I will be just cutting whatever is left. So I'm very sorry I cannot be with you actually in Mexico. I was really happy to go there, but then we had some complications and unfortunately I couldn't travel. Anyway, I got the instructions that I should give a general talk on luminosity that is also accessible for PhD students. So this is what I will try to do. So just to be on the same page, LHC is a synchrotron, which means that we have bunched beams which are accelerated by radio frequency cavities. And basically the radio frequency is synchronized to the movement of the bunches. When we are at full energy, then the radio frequency is 400 megahertz. And this type of acceleration also provides some longitudinal focusing. So this means that we have at the LHC a few centimeter bunch lengths. Now, the dipole magnets keep the particles on a roughly circular orbit. We have alternating arcs and straight sections, and the experiments as well as beam instrumentation is actually mostly housed in the straight sections. There are focusing magnets, quadrupoles, which can squeeze the beams into very tiny cross sections. So in the transverse dimension, we have about 10 to 16 micrometers. And then, so we have a possible of 3,568 bunch locations, which are spaced at 7.5 meters. Basically, this means that we can have collisions every 25 nanoseconds. So the filling scheme has bunch trains, which basically is because the LHC is filled by a series of accelerators, starting from a linear, then a small, the proton synchrotron, a larger, the super proton synchrotron, and then we go to the LHC, which means basically that we have a number of filled bunches after each other, and then some gap between them, and then again filled bunches, which we call bunch trains, and we can identify each bunch crossing with a unique identifier, which we actually use because we measure, as you will hear, luminosity bunch by bunch. Okay, so what is luminosity? Well, luminosity basically quantifies the interaction rate at a collider. So it's basically the gives the rate. If we have the cross section, we multiply it with the luminosity and we get the rate. If it is time dependent, then we call it instantaneous luminosity. And this is important because this gives feedback to the accelerator, to detector operations. And we can also integrate it over time, which will be very important for physics measurements. The bunches can be different, and this is why it's important to actually measure the luminosity bunch by bunch, and which is sometimes called single bunch instantaneous luminosity. We have very, very intense bunches, about 10 to the 11th protons per bunch, which basically means that when they collide, we have multiple interactions per crossing, which we call event pileup, and it could go up to roughly 70 these days. Okay, so why do we need to measure luminosity? This is because we want to do physics, and in order to test, for example, the standard model and precisely measure a cross section, we need to normalize our observed number of events by the data volume that we analyze, which you can see here. Also, if you want to discover some new physics, if you discover, you can measure a cross-section like we did for the Higgs boson. If you don't, you can still put limits on the maximally allowed cross-section, and then with this, you can actually constrain the parameter space of your model. So what is that the physics goals require? For LHC, it's roughly around 1%. I will show you a few examples in a second. So what we actually do is that we measure luminosity real time, which we also call online, with a precision of about 2 to 5%. 2% is the goal for high luminosity LHC. And with this, we assist the beam optimization, for example, luminosity leveling, which is continuously done. at the beginning of each field at CMS and Atlas, but for example, all the time for LHCb and ALICE. And ultimately, after final calibration, we would like to reach 1%. And this is in order to not have luminosity as the dominant uncertainty. Even with 1%, as I will show you, it will still be the dominant uncertainty even for the Higgs boson at high luminosity LHC. Now, let me show you a few examples of the effect of luminosity uncertainty on physics measurements. So this is a study for high luminosity LHC with 3000 inverse femtobarn, and you can see that the total uncertainty, excluding luminosity for the Drellian lepton pair production, is about 1%. So if you have a 1% extra uncertainty, then you are still just increasing your total by about, I don't know, 0.5%, a bit more. But if you don't reach this 1%, then basically luminosity will determine your precision completely. Now let's go to something higher mass. So what about top pair production? If we assume that we have improved performance, for example, at phase 2, which basically means that we have about a factor 2 improvement on the jet energy scale and other experimental uncertainties, then you can see here, hopefully you see my mouse, that the luminosity uncertainty, which is on the x-axis, basically determines your total uncertainty, because all the other uncertainties are below the 2% level. If we now go to the Higgs boson property measurements, as this is one of the holy grails at LHC, that you can see that at high luminosity LHC, for the most precise cross-section measurements, so for gluon-gluon fusion to Higgs boson, the luminosity uncertainty, even if it reaches 1%, will be the largest experimental uncertainty. And even if we consider the rather important theoretical uncertainties, it will still affect the final precision. So this is why we say that we want to reach 1% uncertainty, even at high luminosity LHC, and also we would like to reach it, of course, in run-free. So let me go to the strategy of luminosity measurement. So as we discussed, the rate is calculated by luminosity times cross-section. So if we want to have an absolute calibration of our measurement, we have to take a detector, which has roughly linear rates with luminosity, and measure it. And we have to do it in a way that we can determine this proportionality factor. So what we actually do, that we have special data taking, which are called van der Meer scans, where we have really well-controlled environment, and where we can measure the luminosity from the beam parameters, as I will show you. And then if you measure the luminosity from beam parameters and you measure your rate in your luminometer, then you get your calibration constant, which we call visible cross-section. Of course, the main challenge is actually understanding what are the systematic uncertainties that affect your measurement. And then to get the integration over time and bunches, we will have to sum up this measured luminosity for all the bunches and integrate for the full measurement period, which can be several months. So this means that our instrument should be very stable in time. Also, because we measure the calibration constant at very low pileup, typically below 1, and then our physics is done at high pileup around 50, but can go up to 70, 80 sometimes. This means that we have to understand how we can extrapolate this calibration constant from the low to the high pileup region. And also because I showed you that we have bunch strains and we have very high intensities, our detector can be, for example, activated. So there could be out of time effects, background that we have to take into account. Okay, so let's see. So how can we measure luminosity from beam parameters? You can see here. So you take the orbit frequency, which is about 11 kilohertz at LHC. You multiply it by the bunch intensities of the two colliding bunches. And then you have to integrate over the bunch particle densities as the bunches pass over each other. Now, if you can assume that these bunch particle density distributions are factorizable in the horizontal x and y axis, then you can have a really simple equation for the luminosity, which contains the orbit frequency, the intensity of the two bunches, and then the effective bunch overlap widths in the x and y transverse direction. Okay, so now we know what to do. We measure our head-on luminosity from the beam parameters that I will show you how. Measure the rate of the luminometer and then get the calibration constant. Now, typically we do it in very special conditions with low luminosity, single vast separated benches, so definitely no trains. We have also blow up the bunches so that they have a large beam size so that we can basically measure their shape, and we will have a zero crossing angle. I will not talk about that. Now, how we do this famous Vandermeer method. So what we do is that we make a so-called transverse beam separation scan. So imagine you have the two beams. If they collide head-on, then there is a large overlap between the bunches. There will be a lot of interactions, and then you will have a large rate of particles, for example, in your detector. Now, if you separate them and they just basically scratch each other's, then you have much less interactions, a lower rate. And basically, if you measure the rate in your detector as a function of the transverse separation of the two beams, then you can measure this beam overlap width, which is basically the integral after subtracting the background divided by the peak. Okay, so from this we know what is the width of our beam overlap integral. Now let's go to the next. No, it's stuck. Okay, so what we have to consider. So in order to get the visible cross-section on top of these widths, we also have to know the peak rate, subtracted from it the background. And then we also have to know the bunch intensities. So basically, we will have several effects to consider: how precisely we can measure the number of charges per bunch, how precisely we understand the background of the measurement, how precisely we understand the scale of the beam separation. We get the nominal scale based on the beam currents, and then we have to measure it in our detector's coordinate system. We have to understand whether this non-factorization assumption is true, and because we have two very intense bunches, they will actually interact with each other, which will change their separation as well as their shape. Okay, so how we can measure the bunch intensity? We have several instrumentations. This is not done by the detectors, but actually by LHC. The total current can be measured by the so-called DC current transformer. This is the most precise measurement to the about 0.1%. And this includes all the bunches, all the charges in the bunched and non-bunched, unbunched charges. Now, what I mean, let's look at this picture here. So I mentioned to you that we have these RF buckets. We have the 400 megahertz RF frequency. For each of these, we have basically one bucket. We only fill at the LHC maximum at every 10th, which will be our filled bucket, and this will be the bunch that is filled. And then next to it, in each bucket, we could have some residual charges, okay? So basically, when we measure with this DC current transformer, we measure everything. Now we want to measure actually the charges per bunch. So this means that we also have to measure it in small time windows. And this is done by the fast beam current transformer, which is basically a wall current transformer. And this also includes the satellite bunches, which are in the same 10 buckets that belongs to our field bunch, but it does not contain the gauss, which are in the so-called unfilled bunches. Now we have many other monitors, the beam quality monitor, the longitudinal density monitor. I will not go over that, but these can actually measure and cross-check each other. The main bucket where we have our physics collisions happening, as well as these so-called parasitic bunches. And then we have to correct our measurement to take this into account. Okay, so now we know our intensities. We have to measure the distance between the two beams, it's their separation. We have so-called beam position monitors. There are two types at the LHC. One of them is sitting in the arcs where the beams are deflected by the dipole magnets. And the other one is sitting close to the interaction point at the last focusing quadrupole magnet. Okay, so these both can measure the orbit position with respect to the nominal position that we expect, and we can use this to correct the beam separation in our measurement. Also, as the bunches collide, we can track the movements of the bunches by looking at the beam spot, or sometimes it's called luminous region. So basically, where most of the collisions happen, we can reconstruct the vertices, the interaction vertices, and basically the mean position of the vertices gives you the position of the luminous region, and this is basically calculatable from the position of the two beams. Okay, very well. Now, we have the positions. Now we have to know what is the scale that the LHC uses to give us the beam separations. This is basically calibrated in the laboratory by looking at the magnet currents. And what we do is that we perform special scans where we, for example, separate the two beams and then move them in the beam pipe together. And as we move them together, we move the beam spot position. And by measuring the beam spot position with our tracking detector, we can actually calibrate the nominal scale of the LHC separation to the actual scale in our detector. Okay, and then we get a scale factor, which will be used to get the correct separation between the two bunches. Now, I also mentioned to you that if you have two such intense charged particle beams, they will interact with each other, basically just with the well-known electromagnetic interaction. There are basically two effects. One of them is a kind of coherent effect, where the two bunches get at a larger separation, and we call deflection, and this can be analytically calculated. There is a more tricky effect as well, that the shape of the bunches, so basically the particle density distribution, will be distorted. This will affect the overlap integral, and therefore it will modify the rate. And this cannot be analytically calculated. This is simulated by different programs. And actually, just a few years ago, we learned that for 10 years, we have calculated this, this effect incorrectly. And then all the measurements, all the luminosity measurements had to be shifted. So now we know all of these effects. We can calculate the beam deflection. We can calculate how much the shapes distort and what is the effect on the luminosity. And you can see here that if we calculate this effect, and there is actually about 0.4% effect on the luminosity. Now, I mentioned to you that we want to measure luminosity by 1%. This means that basically all of the uncertainties that I mentioned to you should be controlled to roughly 0.2% level if we really want to reach that. Now, we have discussed a lot of different effects. And one thing that we noticed is that if we look at the beam positions, when we make, for example, the VDM scans, and then change the separation of the two beams, then there is a kind of a residual effect, and it seems to be always the same in every scan. And it turns out that because of the beams are steered by magnets, there could be some kind of hysteresis effect, some magnetic nonlinearity that actually changes the separation because of the memory in your magnet. And this can be measured. And actually, this is right now one of the largest systematic uncertainties, sometimes even reaching 0.8% range. There are many measurements in the laboratory, also special in special beam conditions. We took some data this year, so that we can understand this much better and can control it also at the level like we can do all the other ones. Okay, so all these studies that I mentioned, for example, for the beam-beam interactions and for these magnetic linearities, this is done in the LHC luminosity calibration and monitoring working group, where actually the different collaborations and also LHC accelerator experts work together to reach the ultimate precision that we can. And that means that basically this working group was the one that could improve the beam-beam interactions, and now our uncertainty is at the level of around 0.3%. Okay, the last uncertainty I would like to mention is the so-called transverse factorization. I mentioned to you that in order to get this very simple formula with the effective widths, we had to assume that the beam particle density function is factorizable to an X and a Y component. Now, if you have Gaussian distributions, then this could work very well. Unfortunately, even when LHC experts are very careful and tailor our beams at the injection chain to get as Gaussian as possible beam, we do not have this factorizability actually exactly true. This means that we have to actually measure how large is the bias from this assumption. And because this is one of the largest uncertainties, in some measurements it was even up to 2%, the different collaborations came up with many methods to measure it. So CMS collaboration have a special scan where they keep one beam stationary and then move the other beam, measure the rates, and basically use this beam to get the shape of the other one. And with this, by doing the measurement for both beams in both X and Y direction, you will have 4 rate over position measurements. You can make a simultaneous fit and you can extract the shape of each beam separately. And if you extract the shape of each beam separately, then you can actually calculate the beam overlap integral, and you can see how different it is if you just make the calculation by doing the one-dimensional fits that we did before. Okay, so this is one method. There are many other methods. For example, you can look at the luminous region, so the beam spot, and see how when you move the beams with respect to each other, the position of the beam spot and the width of the beam spot moves. And from this, you can also extract the beam shape. And basically, by extracting the beam shape, we can measure this correction. This correction is typically at the 0.5% level. And you can see here from CMS that with the two different methods, so from the beam imaging and this luminous region method, we measure the same values. And as time progresses, sometimes this stays the same. But in other fields, we have seen that actually this correction changes in time. The correction can also change, as we can see from the Atlas measurement, change from bunch to bunch, because all the bunches can be different. They can have different shapes. So this basically means that we have to monitor during the full measurement period how the factorization effects change and how they affect our measurements. One very interesting idea came from LHCb collaboration, when they decided not just to do scans in the X and Y direction, but actually do a so-called two-dimensional scan, where you separate the beams both in X and Y direction in different amounts, and then you basically get the full shape of your beam overlap region. With the scan that they devised, they can basically probe about 86% of the full integral. Now, because we want to measure with better than 1%, of course, there is still quite some work to do the extrapolation to the remaining 14%. Now, many of these measurements are not practical if you do them in heavy ion collisions, and therefore CMS made something like a 2D scan, but actually just doing kind of a diagonal scan when you move the two beams at the same time so that they change the separation in the X and Y direction at the same way. And also scanning kind of in an offset way, where in one direction you have a beam separation, and then in the other, you change the separation between the two. And basically doing then two-dimensional fits, this is something you can even do in heavy ion collisions, and then you can measure also there the XY correlation, XY non-factorization. Before this method, we had a very large uncertainty in our heavy ion measurements, about 2%. And with this method, we could go to about 0.5%. So this is very useful and interesting. Okay, so we did all the measurements, and now we want to see whether we have corrected all the effects and whether we can have a precise measurement. And for this, what we do is that we measure bunch by bunch the visible cross-section, so the calibration constant. And we also have several VDM scans, basically repeating the same scan several times and remeasuring the calibration constant. And basically what you can see here from the Atlas collaboration is how the visible cross-section changes from one scan to the other. And basically, this measures whether we have some uncorrected uncertainties which are related either to the shape of the beams which change with time, or maybe with the detector, whatever it can evolve. And another interesting cross-check that you can do, if you measure the calibration constant for several detectors, and then with each of them calculate the luminosity in the regions of the van der Meer scan when you are head-on, then you can compare in the same field where you derive the constant, whether it works properly and whether the different luminometers give you the same luminosity. You can see here from CMS such a cross-check, and you can see that basically better to 1%, they do agree with each other, about to 0.5% in this example. Okay, so we have now discussed how we can calibrate a luminometer. Now, what kind of luminometers the different collaborations use? What are the important questions? Whether your luminometer is stable in time, we will have to integrate over many months. Whether it's linear, because we calibrated them at low pileup and use them at high pileup. Whether they are fast enough to provide a bunch-by-bunch measurement, or only an orbit integrated one where you sum up all the bunches in the accelerator, and also whether it is a statistically powerful detector that you can calibrate in the VDM method at low pileup. So whether you have enough hits even at low pileup, for example, in your detector. Now let's see a few examples what the different collaborations use. So this is Alice collaboration, who uses scintillating counters, Cherenkov counters, and the 0-degree calorimeter. So basically in every of these detectors, it counts heat in the detector, and use this to measure the luminosity. Now, in the case of Atlas, their main luminometer is a Cherenkov counter. It's called Lucid. And this detector is very well calibratable in the VDM scan, but unfortunately, it is not very linear. It has actually a non-linearity of about 10% from the VDM to the physics. This means that they have to use some kind of linear counting algorithm, for which they use the track counting, to correct for this non-linearity. So what Atlas does as the main measurement, they use a VDM calibration for the Lucid and then correct its rate by the inner tracker track counting algorithm, which unfortunately cannot be calibrated at VDM because there is not enough rate. So basically they combine two methods to get one measurement. And this is then cross-checked by, for example, measuring the current down in the hadronic Thalkal PMTs, or by measuring the ionization current in the forward calorimeter. So with these detectors, they can measure the luminosity and cross-check the three measurements with each other, whether they are stable, whether they are linear. In CMS, we have actually many luminometers. We have online real-time luminometers, which can be calibrated in VDM and also show linearity at high pileup. For example, the pixel luminosity telescope, which are basically 3 layers of silicon pixel detectors, and they measure coincidences as the particles pass through. We also have a silicon pad detector, which is called beam condition monitor, which just counts hits on the silicon pads. We can use our hadron forward calorimeter either to check the occupancy, how many towers of the calorimeter are hit by particles, or we can sum up all the transverse energy in the calorimeter and use that for luminosity measurement. We also have two so-called orbit integrated measurements. One is actually a radiation detector, which measures the ambient dose equivalent rate in the CMS cavern. And the other one is the muon drift tubes, where we can count the stubs in the detector. This is reconstructed at the level 1 trigger, and we can count these level 1 trigger primitives to measure the luminosity. One of our most stable measurements is with the pixel detector, where we reconstruct the clusters in which energy is deposited in the pixel detector, and basically we do a cluster counting. LHCb also uses many different detectors, basically counting hits on silicon pads, summing up ET as we did. And their most precise measurement, which is actually seems to be the most stable, is using their very, very precise vertex locator detector, which can go very close actually to the beamline. And there they can count tracks and vertices, not online, but offline. Now, if we are at LHCb, this vertex locator has a really outstanding spatial resolution, to a few micron level. And this also means that they can reconstruct interaction vertices between a beam and the residual gas in at the interaction point, or they can actually inject gas molecules and use this to get the shape and the position of single bunches. Now, this is really unique. None of the other experiments can do this at the LHC. But this means that LHCb actually has an alternative method to measure luminosity, not only the van der Meer scans. Now, how this works? Basically, they can measure the interaction vertices, both for the beam gas and for the beam-beam interactions. And from this, they can basically get all the properties of the different bunches. And then this can be used instead of the VDM calibration to measure the widths of the bunches and to measure the overlap integral between the two bunches. Okay, so we did the measurement. We have calibrated our detectors, and now we want to integrate. And for this, we have to think of three effects that I will show you. One of them is the so-called out-of-time effect. Now, what is this? If you have a detector and you hit it with particles all the time, then some of the isotopes will activate itself, will get activated. And that means that there will be a so-called afterglow. There will be particles coming out of the detector, which cause hits after the main bunch crossing. If you have high intensity, you will have a high afterglow. This is basically proportional to the luminosity. And there are two types of afterglow that we could see. One of them affects only the next bunch after a bunch crossing. And this could be late particles, for example, low momentum particles, or time work of your electronics. And then you will have this exponentially decaying afterglow, which will affect many, many bunch crossings afterwards. You can see, this is one of our detectors, a silicon PET detector, how this looks like. You have the luminosity in the first bunch. In the second bunch, you see that there is still a reasonably large component, and then it will decay exponentially. And in order to reach very low levels, you need about 30 or 50 bunch crossings to pass by. Now, for our pixel cluster counting, this is actually a really important effect. You have something like a 9% in the next bunch with respect to your luminosity. And then with this exponentially decaying tail, you have another 4% of the luminous signal as a background. And this has to be measured, this has to be subtracted. This is different for every detector that you use, but this is really important to get it right. And after we measure this from the data, basically fitting the so-called single bunch response function that you see here for the BCM1F, then you can subtract it. And how you can say that this is properly subtracted, if you look at the empty bunches. So here what you see, this is the bunch crossing ID. The blue points are the measurements without any correction, and you see this long tail. Now, after correcting for this afterglow, you can look at the values in the filled bunches. This is decreasing by about 15%. But if you look at the empty bunches, you see that now you have 0 there. So we have managed to properly subtract this background. And basically we can do this with about 0.3% uncertainty. Yes?
10 minutes left.
Yeah, I will finish. Okay, so for the corrections, we also have a change in efficiency and the possible nonlinearity. Now, how you can measure this? There is something called emittance scans, where you basically have mini VDM scans in physics conditions that you can measure the visible cross-section. Now, these are not very precise measurements, but the relative scale is quite correct, which means that if we normalize it to a measurement at the VDM campaign, then we can see the relative change in our visible cross-section by analyzing these mini VDM scans. And this is how, for example, we can correct for efficiency losses. This is the BCM1F detector. What you see here as efficiency, this is basically in the change of visible cross-section for the different measurement periods. And then if you look at the different periods, you can basically make a correction for the efficiency. And then this way, you can have a more stable measurement. The other thing that you can do is that you have emittance scans at the beginning and at the end of the fields. But because of the luminosity burn-off, the instantaneous luminosity will be roughly half by the time we arrive at the end of the field. And if we have that, then this means that we can measure as a function of the instantaneous luminosity, the change in the visible cross-section, and this gives you an internal independent calibration for the linearity. So after you do all these calibrations, you have to understand if your detectors measure the same thing or there is any residual nonlinearity, for example. And other collaborations actually do not use as extensively emittance scans as we do. And then what they do is they basically have kind of a calibration transfer measured very close to the VDM campaign, where they compare the measurements of two different luminometers. For example, in the case of Atlas, they compared the measurement of the lucid Cherenkov counter with the track counting that I mentioned to you. And from this, you see that this is really nonlinear. This is how they get the linearity correction. And then after this linearity correction is introduced, they can check whether during the time we take data of full year, anything changes, because they measure, for example, the lepton pair production with respect to the luminosity, and they see that, okay, there is a small slope, but it seems rather linear. And this way, basically, we can check by either comparing different luminometers or comparing a luminometer, some physics well-known process like Drelian production, whether our luminosity is properly linearly measured. And we can even check, for example, as we did in 2016, whether the linearity changes in time. And you could then see how precisely you can measure this and put some uncertainty on it. And then the last thing I want to show you is the time stability. After you made all the corrections, you can check how the luminosity is measured by the different detectors. And I mentioned to you that the most precise one to date is the Velo track and vertex counting ratio, which is over the run to, so over 4 years, had a 0.2% RMS between the two measurements. Of course, we have to remember that LHCb works with low intensity, low luminosity. They are leveled to a low level of luminosity. So at that things are a bit easier, but nonetheless, this is really, really the best stability measurement that we have so far. For CMS, Atlas, and ALICE, typically we get stabilities around 0.51%. So now we can put everything together. The main uncertainties are the scan-to-scan reproducibility. So basically, the effects that we cannot correct between the measurements, the knowledge of the orbit positions during the scans, which affect the separation and therefore the measurement of the effective beam overlap region. The non-factorization effect that I mentioned to you, that whether the shape of the bunch proton densities are factorizable in X and Y. And then the calibration transfer, so the linearity that I just explained to you, and the detector stability. And if we put all of these together, then you get to some results like this. So the best measurement to date is from CMS in 2016, high luminosity proton-proton collisions at 13 TeV. This is the published result. All the published results are given by boldface. You can see that there are not many. Basically, there are 4 numbers here that are published. All the rest are preliminary results. And the worst measurements are roughly in the 3-point-something region. So basically, we can say that we are very close to reach with our final calibration the goal of roughly 1 or 1.5%, even in run 2 or hopefully run 3 of LHC. And that means that with better instrumentation, many collaborations work on better luminosity detectors at the high luminosity LHC, we can hopefully reach our goal of 1%. And thank you very much. Questions?
Thank you, Gabriela, for your very interesting talk. We have a few time, but we have some time for 1 or maybe 2 quick questions. Anybody wants to ask something to our speaker? Here or remotely? I don't see any hand raised. Or here? Carlos. Yes, please go ahead.
Hi, Gabriela. You said that the LHV uncertainty is, well, they have the more stable measurement, right? But there you have, it's 2.0, right? In the last slide, the previous to last slide. And
yeah, because there are other sources. So this is the stability uncertainty, how stable that measurements are. But of course, there are many other sources that I can, unfortunately, LHCb doesn't actually publish these measurements. But if you look at, for example, the CMS or Atlas measurements, you can see that there are many different uncertainties that I went through. So the 2% comes because I suspect, I don't have the details what the 2% is dominated by LHC, but I suspect that some others like factorization or other sources give significant contribution.
Okay. And just one last question. It used to happen that when the luminosity was published on the LHC monitors and so on around CERN, Atlas and CMS will always show different luminosity, either instantaneous or integrated. Is that has changed with all this work that you have done in this group? Or is it still, you can...
So there are 2 things here. One is that it is not at all ensured that we get the same luminosity. You know that now LHC uses beta star leveling, and the precision of the leveling might not be, to the percent level. And the other thing is that what you see on the monitor is typically our real-time measurement. What we want to achieve the 1% with is after final calibration. At run 3, we say that real time we can measure to about 5% precision. And this means that if you see, a 5% difference between Atlas and CMS, this could either be because of the measurement uncertainties, but also because LHC might deliver different luminosities to the 2 experiments.
Okay, thank you.
Welcome.
Thank you, Carlos. Anybody else wants to ask something? Any other question? Remotely, the ones connected on Zoom? Well, if not, let's thank again Gabriela. Thank you, Gabriela.
Thank you very much.
Well, our next talk is precisely by Carlos Chavez, Dr. Carlos Chavez, who's going to talk us about muon experiments.
So, lo tengo que agarrar todo el tiempo. Sí. Ah, okay.
No,
Oh, entonces,
es nada más el apuntador.
y tengo que
Sí.
sostener esta, okay. Hello, thanks for the invitation. It's a pleasure to be here and see some old friends as well. Okay, so I'm going to talk about these some muon precision experiments, and oops. No funciona esto. Oops. Ahí está, ya. Creo que ya. So this is part of the group that I work at Liverpool University. We are involved in several muon precision experiments. G-2, mu EDM, and some charged lepton flavor violating experiments. So just as a disclaimer, I'm not part of G-2, but I work on a couple of these experiments, and I will describe later. But I'm kind of presenting on behalf of people from Liverpool that work on G-2. Graziano Benanciano, and he's the spokesperson of G-2, is now joining the group in Liverpool. Okay, so let's just start with the basic of the standard model. So as we know, it describes particles and their interactions via electromagnetic weak and strong forces. And also the way that we order these particles, it constitutes all the matter that we know, and we group them usually in 3 families. But we don't know why they are associated in these 3 families, okay? So that's something that this program of muon precision experiments kind of trying to give a hint on what's going on this. So as you have heard before, I mean, there are 2 ways of looking for new physics usually. So using high energy colliders, like the LHC, or either future colliders, FCC and ILC, for example. So you design them to search for new high mass particles. But another way to look for new physics is using high intensity experiments, which use lots of particles through and try to make precision measurements using, for example, new low energy effects and so on. So experiments like G-2, mu EDMs, and very decays of latent flavor violating experiments are these kind of other ways of looking for new physics. Okay, so we know the muon is very similar to the electron. It's just 200 times heavier, but it has an intrinsic angular and magnetic moment. But apart from that, it's very, very similar to the electron. Also, we don't know exactly why this happens, right? But it was discovered in 1936 by Anderson and Neddermeyer. They built this type of a small cloud chamber, and they took it up in Pikes Peak in Colorado, and they took pictures with it, and that's how they found the muon with a trace in the cloud chamber. But for 10 years, this particle was confused to be the particle responsible for the nuclear force, and it was not known as the mesotron until another experiment that was carried out by 3 Italians during the Second World War, that they basically disentangled this ambiguity and discovered that it wasn't the Yukawa particle, but a lepton itself. And so a way to look at the properties of the muon in particular, but basically in any charged particle, is looking at the angular momentum and magnetic momentum of charged leptons, for example. So it's given by this quantity here. So in any in a planar orbit, you can have this angular magnetic moment, and so the ratio between the two is called the gyromagnetic ratio, called G. Classically, this will be 1, okay? But for elementary particles of spin 1/2, like the electron and the muon, the Dirac equation predicts G to be equal to 2, okay? So what we call the magnetic anomaly is defined as A equal to G minus 2 over 2, okay? So according to Dirac, if G is equal to 2, then A is equal to 0. So, okay, so that's the magnetic anomaly, and that's basically what measures G minus 2 experiment, for example. But before that, we can also look at the magnetic moment of the electron, okay? And this was done in 1948, okay? And it was measured to be very, very close to 2, okay? But it says here the possibility that the observed effects may explain by perturbation is precluded by consistency of the result as obtained by various comparisons, and also on the basis of the theoretical consideration. So basically, because it's not equal to 2, that already hints that there is something else going on in influencing the value of G. And so this was a very amazing success by QED that predicts the difference. Basically, that A is greater than 0 and G is greater than 2. And so this was the very beginning of the basically putting the right foot on QED. And it's all what we know now is all about the vacuum, right? Vacuum is filled with pair of particles that exist in tiny amounts of time, virtual particles. They pop and they disappear. And so they produce tangible effects on the physical phenomena, okay, that we observe. Okay, so if there was no this vacuum structure around, then you will have G equal to 2, but because there exists this, we expect to have it to be different from 2, okay? So that's due to all these big virtual particles appearing in the vacuum and disappearing. So this, here I showed the asymmetry, the value of A mu. This is basically the calculation, okay, the most one of the most precise calculations by the standard model that includes QED, hadronic and weak components. And this was published in 2020, and is one of the most basically arduous programs to calculate the standard model of value for A, okay, for the muon. So this goes all the way to 0.37 parts per million, okay? So this is an amazing work that theoreticians have done throughout decades of work. And the idea is I show you this calculation here, but I'm gonna try to show you how do the experimental side of things has evolved through time with a bit of history to get to compare against this value, but from the experiment side of things. Okay, so here, unfortunately, I have this a PDF version of my talk, and in the PowerPoint presentation, this has an animation, but basically what I wanted to show here was the frequency in which the spins move ahead of the momentum in a magnetic field. Okay, it's called the anomalous precision frequency, WA. Okay, and for these two. So basically, when we don't have an anomalous momentum in anomalous precision frequency, basically when the if you have a muon with a momentum going in this direction, following the orbit of the storage ring, and the spin of that muon carries in the same direction all the time, as basically aligned with the momentum of the muon, then you will have G equal to 2, okay, and the anomaly equal to 0, okay. When G is greater than 2 and A greater than 0, then this is when you see that as the muon moves along the storage ring, for example, then the spin will move usually ahead of it. So it will move a little bit faster, will rotate faster than the momentum of the muon, and so it will be misaligned, and that will produce an asymmetry that you can measure. Okay. Okay, let me see if we can go. So let's have a bit of history on this G-2 experiments. So here's what we have. So muons are produced polarized in the forward direction. So you have, for example, pi minus going to decay to muon minus and 3, no? And then the decay, this decay with the information where there has been was time decay. Okay, so what we measure is the mean momentum correlations fundamental to all these anomaly experiments. Okay, so depending on the momentum and the spin of the positron in this case, if it's coming from a mu plus, you will see where the spin of the muon was at the time of the decay. So if you see high energy positrons have a momentum along the muon spin, and the opposite will be true for the electrons in mu minus. So we detect the high energy electrons, okay, and the time dependence of the signal of these high energy electrons tracks the muon precession. So the parity violating production, the case of the muon, basically, here was an experiment by Li and Zhang, okay, that basically, if they hint that they were just looking at the parity violating effect, but they noticed that if the rate of high energy decay electrons is time modulated by the precession of the magnetic moment with a frequency which depends on G here, okay, then they were able to see that there was when the momentum was aligned with the spin of the muon, then this was favored. The decay of high energy positron was favored, and when it was misaligned, then is disfavored. So you see more positrons when the momentum and spin are aligned, and when they are misaligned, then you see less positrons. Okay, so and that's what basically. And the next year, Gerwin Lederman and Weinrich, they measure this asymmetry, which is the typical type of wiggle plots. So, but this was the first wheel plot. And as you can see here is G of the mu, okay, equal to 2 with an uncertainty of 5%, okay. So they measure these positrons, and they know when they are aligned or not with the decaying muon. And so the next experiment, the next year actually, in Liverpool with a cyclotron, and they also measured the same variation of the rate of positrons, and so they measured this much better with a 0.7% uncertainty on G. Okay, so these experiments were measuring G only because they don't have sensitivity for more than that, and then. But also they argue that the value of G itself should be sought in comparison to the precession of a cyclotron frequencies of muons in a magnetic field. The two frequencies are expected to differ only by the radiative corrections. So basically they're proposing here that you need to measure the frequency also of the cyclotron very precisely and the B field basically, in order to basically disentangle to go further in uncertainty. And this is what, the next set of experiments were to set out to look for, basically measure A now. And with the muon G-2 CERN experiments that ran from 1962 to 1979, okay? These experiments measure the relative, the spin relative to the momentum of the muon, okay? So the first one was the first CERN experiment, CERN-1. And they basically inject muons here into a magnetic field tube, and then the muons start orbiting because and moving forward this way because there is a drift, there is a small gradient on the magnetic field, and when they go around about 1,600 turns of the muons, then they decay. And then you measure the positrons there. So we just track the muons at a large gradient polarization monitor, and then you stop them here in this monitor here. The time in the magnetic field was measured by counters that you have. And to measure the time-dependent forward and backward asymmetry of the decay is what you measure. So you look at how many of them decay backwards and forward, and that gives you this wiggle symmetry. Okay, and this was sensitive only to 4 times 300 parts per million, and it's comparable only to second-order corrections on QED. Okay, so remember that equation that I gave you about A mu. So this was one of the first calculations with QED corrections on them. So the theory was very close to the experiment too. But then this was just the beginning, because then instead of using that type of tube, then the next experiment, this is the first storage ring that was used to basically store the muons and look at how the spin of the muon process with respect to the momentum of the muon. And then again here you measure this wiggle in the rates of positrons that you see, and then you extract the frequency from these plots, the precession frequency. Okay, so that was the second CERN experiment. So now they realized that in order to be more precise, what they wanted to do is that they were having problems in the second experiment at CERN. They had problems with how to confine the muons vertically, and so they that introduced huge systematics in the analysis, and so they decided to introduce electrostatic quadrupoles. But this basically you're introducing this term here, an electric field basically that you introduce. But one of the great ideas was this idea of the magic momentum. Basically, if you put the muons at this momentum in the storage ring, then these terms can cancel, and then so you get rid of this term here, okay, and you just get again this relationship. So you don't worry about the electric field anymore, but still you need some corrections for this, okay? So this had a mu been, say, the stands, yeah, well, if you had this value of a mu that it was, let's say, 100 times smaller than this, then you will have to have a different magic momentum that it will have to be about 30 GeV, which is huge, right? So we're a bit lucky that this wasn't the case for the muon. And so this is the third CERN experiment that this uses, well, injects pions at 3.2 GeV, and then this use a proton to muon decay to kick the muons into a stable orbit here. So you have them going around. And this was the last experiment, which it was very successful. It still had problems with you inject the pions and you have lots of background and things like that, but it wasn't as bad as the previous experiment. And here is the plots that they got with this new storage ring. And as you can see, the parts per million, the precision is 7.3 parts per million, and the theory also was competitive with it. Here you start being sensitive to hadronic vacuum polarization contributions in the calculation of in the theoretical calculation of the anomaly. So yeah, this was a huge success for CERN. However, there were further developments in theory, on the theory side as well, and there was appetite for trying to go even further on this. So there were two major experiments in the US, one at Brookhaven and Fermilab. Okay, the one from Brookhaven started in 1984 and finished in 2001. So at this date, QED was calculated fourth order already. Hadronic uncertainties were greatly reduced. So there was time for start a new experiment that will go even further in precision. The improvements that they need to have with respect to the CERN experiment was that they needed much higher intensity, superconducting coils, circular aperture, all these things, inject the muons into a ring with inflector and kicker, so to avoid the flashes of background that they were producing at CERN. Yeah, and so also you need to know the B field very precisely around the ring. Okay, so they have in situ and NMR probes to measure the B field, the magnetic field in it. So this is the technique that they use mostly. So yeah, you inject this. Well, you have protons on a target, and then you produce pions at this energy. They decay, and then the inflector put the muons into the ring, and then it stores them there and go around. So yeah, you have all these new, well, this particular for the Brookhaven experiment. So yeah, you're interested on this again, extracting this precession frequency of the muon. So yeah. So so you look at the positrons and electrons from the muon decay, okay? That's what you detect. And in this case, if the spin forward is when you produce the higher energy electrons, and spin forward, they are less energetic. So you have these calorimeter stations that measure very good timing and energy, and so you can distinguish between the two, basically the high energy electrons or positrons but then you can correlate the difference when the muon, the momentum of the muon is, well, the spin is aligned with the momentum or is misaligned with it. And so this is the wiggle plot that they produce at BNL. And again, here the precision went even further. Now we are at 0.54 part per million. And And this is the theory calculation. So it's again much work went into all these calculations too, but also into the experiment. And now you have electroweak and hadronic light by light contributions to this calculation here. So it's also a synergy of you have parity of experiments going even further, but also the theoretical calculations going keeping up with the precision needed to compare. So yeah, so here's the difference between two. And at that time, when the BNL experiment finished, it was 3.7 sigma difference between the standard model and the experimental result at BNL. So yeah, there was a hint for new physics, but at that 3.7, people get excited and other people just don't care. So there was. Here is kind of the story of this that I just mentioned to you, all the BNL experiments up to the last one here, and the contributions, the sensitivity that they are according to their sensitivity experimentally, and the precision experimentally, and what they can probe in terms of the theory. Okay, so now can see the title, but so this is now they. For those that don't know, the BNL experiment was dismantled, and the ring was taken to Fermilab. And yeah, this actually was in 2013, if I'm not mistaken. So it's not long ago, less than 10 years, when they moved the ring from BNL to Fermilab. And in less than 10 years, they produced quite a lot of new results. So this is the new ring at Fermilab now. And they have lots of new things that they didn't have at BNL. So now they have 24 calorimeter stations located all around the ring, better NMR probes to measure the more precise the B field along the ring. And also one very important thing was to have tracking tracking stations here. They use these very nice vacuum trackers. One these are very thin straws with gas in them. Okay, and then when the positrons or electrons go through them, they ionize the gas, and then the signal gets collected, the charge gets collected by the anode there's a wire in the middle of the straw, and that's where the charge gets collected. So these were produced and made in Liverpool, or at least half of them of these trackers were made in Liverpool. So this was a huge improvement on the BNL experiment, because allows you to measure and correct for asymmetries in the beam, basically. And then you can also measure very precisely the decays of the positrons too. So you can actually make the whole analysis of those wiggle plots only with these trackers, for example. Well, before you were using also the calorimeters to do that too. So, and also, yeah, this is also very good to understand the beam dynamics, the muon beam dynamics here, because that's very important for systematics, especially. And so here's what they measure. They measure these two, the ratio of these two, the muon precession frequency and the magnetic field. The Poisson precession frequency, basically, and these other quantities are well known. So, but then it's quite complicated thing. So these are the wiggle plots that they get at Fermilab in G-2, but you have to correct several parts of this. Okay, so you have beam dynamics corrections, you have muon beam distributions that you use the tracker to do this, and also the magnetic fields. Okay, so they have really clever ways of now mapping the magnetic field around the storage ring. So yeah, these are quite complicated analyses, but they're very nice. And so these are the difference between the Brookhaven and the Fermilab results. As you can see, the precision is much better at Fermilab with all these improvements. Yeah, they also have a lot more data, but mainly the improvements in the beam and detector are the ones that reduce the systematics, and also new people trying to join in these experiments, which is also brings new ideas. Okay, so now this is what I was talking about earlier about getting excited or not. So with the new measurement, the Fermilab of round one of the data that G-2 has, it came out with this result. This is the standard model on the left here at the bottom, and on the right you have the BNL result and the G-2 from Fermilab. And if you combine the two, you have 4.2 sigma. So still the hint is there that there is new physics, the precision is getting better, and it will get better. This result will come in the next year or so with more data from the Fermilab experiment, and so it will reduce the systematics here as well, because they understand much better their systematics now. So so this is the difference between the experiment and the standard model here. As you can see, it's very small, but it's 4.2 sigma the difference in terms of statistical significance. So one of the things is we're definitely waiting for more results from the G-2 experiment in that sense. So is this new physics or not? I mean, that's the big question, right? We want to answer. And for that, we also need another experiment or some new ideas. This is an experiment at J-Park that will also measure G-2. And also it will measure some other parameters, but especially G-2. And it's a completely different design, different idea. And so this will be coming to, well, it's being built right now. And I believe this, I can't remember the timeline for this now, but soon they will produce some results of this. So it's a completely different design. They have this long decay chain here of beam line, and then the positrons will decay inside here, and you basically confine them, and you have positron detector chambers here, and that's where you measure your positrons, and you find out if the muon spin was aligned or not with the momentum of the muon. Okay, so again, from the theory side, just before in April 2021, before the result of the G-2, there was a new published result for. So this is the BNL and Fermilab result here. And just 2 hours before they released this result, basically there was this collaboration from Lattice QCD that produced a result that basically kind of say, okay, well, there is no tension between the standard model and this, but actually basically the lattice calculation and this dispersive approach of the standard model, which are these ones here, are not complete. There's a tension between them, really. So some people say that, oh, this calculation, is telling you that there is nothing new here in this result by the G-2 collaboration, but actually they need to pin down why is the difference between these and these results. Okay, and most of it is due to hadronic vacuum polarization. Basically, that's the hardest part of all these to calculate, and because of that, there is a new experiment actually that is trying to measure the hadronic vacuum polarization for A mu, by basically looking directly. This is an experiment at CERN that will be very soon start taking data. It's using silicon strip modules from CMS and some calorimeters also from CMS. So what happens, you inject very, very high energetic muon, and then you see a decay. But basically, interact with an electron in a target, and then you measure the angular correlation of the muon and the electron, and that gives you a precise measurement of the shape of the differential cross section of this process, mu e, elastic process, and that gives you very good understanding of the hadronic vacuum polarization. So experimentally, people are trying to also figure out what's going on there in the hadronic vacuum polarization contributions to G-2. So now that's kind of okay, perfect. So now there are another set of experiments. So the muon EDMs, in this case, there is one at JPark being prepared, and also Fermilab. These are two storage ring based experiments. So Fermilab with G-2, they claim that they can also measure the muon EDM, okay, but they have to modify the ring a little bit. But I'm going to show you also this new experiment that is being prepared at PSI, Paul Scherrer Institute in Switzerland, using a frozen spin technique. Okay, so the muon EDM signal would be a new, discovery of new physics, basically. There is non-EDMs in the standard model. And also it could explain the matter dominance in the universe. As I mentioned, can be tested in storage rings, but also in dedicated experimental setups that I will mention, for example, for the mu EDM experiment at PSI. So you have a magnetic field and you have a muon going around, so you expect that if you put also an electric field, then you will if there is a electric dipole moment of the muon, then it will couple to that electric field and it will start precessing in a different way. And you're trying to be sensitive to this new precession, okay, of the spin. So this is just a bit of history on all the different EDMs that have been searched for. So neutrons, electrons, muons. So muons are these ones here at the top. And as you can see, for neutrons, the standard model predicts kind of this level of neutron EDM. Okay, so they are getting very close to it. This is experimental limits. Okay, and also for the electron, they're getting close. Well, relatively close to the standard model prediction. And then here the muon is still way back. See, there is 10 to the 18 difference between the two, while the other ones are much closer. And so that's why they're trying to address now, try to bring down these limits of the muon EDM. So yeah, sorry about this. There's supposed to be an animation here, but to show you. But what happens is that you're trying to look for this precession frequency. And if you are in these are cramped, a few slides cramped together. But what happens is that as your muon goes into around the storage ring, if you so the spin is precessing due to the magnetic moment, okay, because you have a B field upwards, but at the same time, if there is a magnetic field, the EDM will couple to that. So, and then instead of the precession of the spin of the muon being on the plane of the storage ring, now it will have a slope. And that will manifest itself in those wiggle plots as a different modulation, basically, of the frequency. Okay. So, but then you need to disentangle these. Okay. So, but in principle, that can be done with the storage rings. So that's G-2 and the J-Park experiment will try to do that. However, at PSI, they have a technique that they basically they want to apply an electric field that is opposite that goes inwards into the ring. In this case, the radius of the ring is very small. It's about 0.14 meters, so it's quite small. And you apply this electric field to lock here the spin and the momentum, to lock it on this plane. So the muon goes around like this, but the spin is locked into only this plane. And so if there is an EDM, it will couple to this electric field, and then it will just precess on the upward plane of the perpendicular to the orbit of the muon. So that, that's shown here. So this is, again, this is a nice animation, but so you have the muon going in here, and then with the magnetic field, you drift the muon along in a spiral. And then here you have, in the middle of this, yeah.
Those connected, we had a problem with the projector here in the hole. They are working with it.
People are still connected on some thing.
Just to profit the poll. So I'm enjoying a lot your presentation, particularly the fact that you found time to discuss the muon experiment, where Graziano is so deeply involved. Maybe I misunderstood it, but when you were discussing the new measurement that is expected in a year or so from now from the muon-G-2 experiment, you were emphasizing the reduction on systematic error, but the first result was completely statistically dominated, and I expect the same to happen for at least for the second one. Am I right? Can you comment more on this, please?
Yeah, still the statistics is the dominating factor in the precision. That's right. But they have quite a lot of data they haven't analyzed. You see, the result was basically the first few months of working, of data taking, and they have about, I think it's 4 times more the data at least, but they will keep running, right? So they will. And also they will improve a few more things on the efficiency, for example, in the ejection and things like that. So that will bring the number of muons so they can store a bit more. But yeah, you're right, it's the statistics. But the systematics are very well controlled, right? That's one of the main things. I mean, that also needs to be keep. Yeah.
Okay, Lorenzo.
So essentially, the measurement that is being reported.
Sorry.
So the mu plus. What about comparing with the mu minus?
Yeah,
the CPT test?
Yes. Yeah, I mean, unfortunately, I'm not part of G-2, but Yeah, and they're quite secretive on when they're going to release their, their results and well, not secretive, they just sometimes, these analyses are so complicated that they have to be very careful with how they do them. And yeah, but I know that this is on the cards to come, that data too. Yeah. And also one of the things I wanted to emphasize now that I see quite a lot of students here is that these muon experiments are really nice for students to get involved in. I mean, you can learn a lot of physics on them, and you can really get your hands on hardware, detectors, basically know pretty much all the what's going on in the experiment, which it doesn't necessarily happen when you're working in a big experiments like the ones at CERN, right? You are usually just in a niche area because there are so many people and so on. Here in these experiments, they're quite small, and they need people to do things, and you can jump into any part of the experiment and do a meaningful contribution to the experiment, which is very nice. So if the students are interested, there is ways of trying to get them involved in these experiments. They're yeah, I think they're really fantastic for training people, and even postdocs as well, to get more experience under the belt. Yeah, I don't know how much time do I have left, but I will just go quickly through the last few slides, and yeah. Yeah, I think so. Yeah. So I was mentioning that here in this EDM experiment at PSI, so you have the muon being drifted up, and then you with a magnetic pulse you stop the muon, and then you have it going around until it decays, and then you get the positrons also going around in very small orbits. But here you have to basically an electric field here to these electrodes basically provide this electric field to basically do what I was mentioning here, to provide this electric field that will lock the spin aligned with the muon. And yeah, and then you have pixelated, tracking detectors that will basically tell you how the electrons are decaying, basically. And then you look at the difference for the. So this is the basic idea. So you have the locking of the spin here, and so this is the radius of your, in this case, a storage system, where you have the muon going around. But then the precession due to the EDM, if it's different from zero, then you will see a slow rise of this basically the spin going in this precession in this plane here, and so you will see a slow rise here of your asymmetry of positrons, basically. And by looking at the upper and lower detectors for the positrons, then if you see this asymmetry building up with time, that's an indication that you have an EDM. I mean, obviously, there are some, you could still see an asymmetry like this if you don't control your systematic effects, but that's one of the main problems with these experiments, right? That you need to control the systematics very, very well to be able to say that this asymmetry is due to a real EDM. Okay. Yeah. So yeah, if the EDM is equal to zero, then the spin should always be parallel to the momentum. So to the momentum asymmetry should be 0 too. So yeah. So this is the mu-EDM collaboration at PSI. So I mean, again, here, things are open for people to communicate and try to join. There's still lots of things to do. yeah, so, and usually people are very friendly in this small collaboration. So, so now finally, I just go very good through with these just 2 slides of, so there is another set of experiments. This is charged lepton flavor violating experiments. For example, MEC2, mu2e, COMET, mu3e. So these basically look for forbidden decays of the muon in the standard model. And so these are the current limits on these 3 decays. So this is COMET and mu2e. This is the decay of a muon to electron and a gamma, a photon, and the decay of a muon and an electron and 2 positrons, or well, depending on the charge of the muon here. But then you see that there are, if you observe one of these forbidden decays, then you can, you know, if you can be almost certain there is new physics somewhere interactive in the, basically in somewhere in the loop producing these decays. So this is mu3. This is basically a tracker with some fiber scintillators and also some other scintillators underneath here. But it's basically a 3-stage tracker. This is 1 stage, the central stage, and the upstream stage. And this is the target. So muons get injected, and they get slowed down and stopped basically in this target, and they decay. And then you observe the decay of the muon, and you try to look for 3 electron type particles. And with your tracker. And so the tracker has to be very, very thin in mass. That's one of the characteristics and the problems with this type of experiments. So yeah, you look for this type of signal, okay, without neutrinos, basically. So you need excellent timing information, good momentum resolution, well-constructed vertex. And so your signal will be picking up after the decays of the muon that are allowed in the standard model with neutrinos. So you're looking for these signals here. And your backgrounds are these, basically, misreconstructed electrons and positrons, and also a decay with neutrinos. Okay, so the tracker, this is the tracker system that I showed you before. So you have the central tracker, and then another, we call it recoiling tracker in this side, and an upstream tracker also here. These are the 2 recoiling ones and the central. And then you have scintillating tiles here, and also fibers, scintillating fibers here for timing mainly. And but this tracker is very particular. Basically, the silicon pixels are very thin, are 50 microns thick. Okay, this is the first tracker with these characteristics. It's basically the chips, the silicon chips they can bend basically because it's like paper. So it's quite, and build it together, put it together and read it out is quite a challenge. So here are some of the examples of this. So this is the circuit, the electronic circuit that will read out 18 chips, okay? The chips will be on the other side of this, but these are the circuits, and it's made with aluminum, okay? That's because we want to reduce the thickness of the material in the tracker. So, and it's because aluminum is much less denser compared to copper. So usually you have these, they're called flexes made of copper and Kapton, or copper and FeF4, some you know, the PCBs that you get to read chips, but these are really thin. And so here we have examples of these pixels detectors, and mounted on this type of very thin flexes. We call them high density interconnect flexes made of aluminum. Okay, so the one at the top here is a mock-up for the cooling system that we are trying to investigate, because one of the challenges here is also getting the cooling. So you cannot have much material there. So here are just basically, yeah, this is the last slide. Just telling you that there is a lot of results coming out of from Fermilab, JParc, CERN, and PSI on all these muon precision experiments in the next few years to come.
Well, thank you, Carlos, for this comprehensive talk. Unfortunately, we have no, we are run out of time too large now, so we'll stop here the questions. We encourage you to ask Carlos offline, and probably we will reconvene like a quick 10-minute coffee break instead of 20, please. Thank you again, Carlos.
No sé si hay problemas con la transmisión. Veo como que no hay nadie en el podio, pero
Estamos en el coffee break, yo pienso. Les han de verdad un minutito para coffee break después de la charla.
ok, alguien me está escuchando entonces.
Sí, bueno, yo estoy conectada, no estoy en la sala, pero yo supongo que dieron un momento de coffee break.
O sea, tú no estás ahí, o sea, tú no estás ahí en Puebla, o sí.
Estoy en Puebla, pero no me dio tiempo regresar a la charla, entonces me conecté, porque tuve otra reunión.
Ok.
Pero yo creo que tienen café. Si no, deja pregunto y ya confirmo.
Ajá, digo, nada más para saber porque uno no, como yo estoy hasta Mérida, Yucatán, entonces no sé si...
Sí, déjame pregunto rápido en el WhatsApp, un segundito.
Sí.
Hola Francisco, yo te escucho también.
¿Qué pasó, Roger? ¿Cómo estamos?
Bien, aquí desde
Estoy
Sinaloa.
conectado. Se oye bien, porque luego esta computadora que estoy usando ahorita, el micrófono a veces...
No estoy en la sala, pero yo supongo que dieron un momento de coffee break.
Ok. O sea, tú no estás ahí, o sea, tú no estás ahí en Puebla, o sí.
Estoy en Puebla, pero no me dio tiempo regresar a la charla, entonces me conecté, porque tuve otra reunión.
Ok.
Pero yo creo que tienen café. Si no, deja pregunto y ya confirmo.
Ajá, digo, nada más para saber porque uno no, como yo estoy hasta Mérida, Yucatán, entonces no sé si...
Sí, déjame pregunto rápido en el WhatsApp, un segundito.
Hola Francisco, yo acá no tengo...
Francisco, yo te escucho también.
No tengo...
¿Qué pasó, Roger? ¿Cómo estamos?
¿Qué tal?
Bien. Hola Antonio, tienes un delay.
Se
Creo que
oye
Antonio tiene
bien.
un delay.
Porque luego esta computadora que estoy usando
Oye,
ahorita...
tienes que ser-
está sonando...
pero yo supongo que dieron un momento de coffee break.
Okay.
Es Antonio quien tiene que estar repitiendo
O sea, tú no
la...
estás ahí en Puebla, o sí.
Estoy en Puebla, pero no me dio tiempo regresar a la charla, entonces me conecté, porque tuve otra reunión.
Ok.
Pero yo creo que tienen café. Si no, deja pregunto y ya confirmo.
Exactamente, Karen. Estamos en un loop.
Yo estoy hasta Mérida, Yucatán, entonces no sé si...
Sí, déjame pregunto rápido en el WhatsApp, un segundito.
Pero igual sí, yo creo que si silencian
Hola Francisco,
a
yo acá
Antonio,
no tengo...
ya no hay ningún problema.
¿Qué pasó, Roger? ¿Cómo estamos?
¿Qué tal?
Hola Antonio, tienes un delay.
Se oye bien. Porque luego esta computadora que estoy usando ahorita... está sonando...
Pero yo supongo que dieron un momento de coffee break.
Es Antonio quien tiene que estar repitiendo
Ok, parece que ya terminó esto. Hola, ¿alguien anda ahí?
Yo estoy, pero me da miedo hablar.
Ok, lo que pasa es que no tengo sonido en Zoom, así que lo estaba viendo en YouTube. Ok, en fin. Espero que ahora sí tenga sonido.
Ok, está bien, está bien. Sí, porque yo dije ¿qué está pasando aquí? Que se está encimando esto. Ok, ya pasó.
Pero sí están en el break del café, Francisco, no te preocupes. Ya
Es
van a
la
llegar.
primera vez que hablo en Zoom. Lo que pasa es que en Simvestab usamos Teams, pero ayer mi esposa me estuvo entrenando a usar Zoom. O sea, mis hijos son expertos, pero yo es la primera vez que uso Zoom. Pero bueno, parece que ya está funcionando bien esto.
Ya todo bien. Se te escucha y se te ve bien.
Ah, qué bueno, qué bueno. Igualmente.
Hola,
Ok.
Antonio. Hola, Roberto.
Hagamos el coffee break aquí entre nosotros.
Ok, sí, ¿verdad?
Pues
Yo
sí,
vine,
ellos que están en coffee, nosotros, ¿por qué no?
yo vine a la oficina solamente por eso, Isabel.
Yo tengo aquí mi cafecito también, mire, también.
Ahora
Bueno,
se va a terminar.
aquí más bien tomamos refresco o agua o algo así, algo algo refrescante.
Sí, claro. Pero creo que las cosas calientes como que también...
Hola, yo acá tengo serios problemas con el audio, así que prefiero no hablar.
Ok,
Oh,
no problem.
bueno, pues nos escuchas. Entonces, también Jesús está tomando su cafecito.
Exacto.
Yo estoy con el café ya.
Muy bien. Yo también me lo traje hace rato. Ahí está Roberto también, cafecito. ¿Tú también
Hola,
tienes tu café,
Roberto.
Roberto? Sí.
Sí,
Ahí
yo
está.
tengo
Ese Roberto se trajo, pero todo un termo.
el termo completo. A ver, 2 litros de té. Te voy a echar.
Gusto verte, Roberto. Qué bueno verte.
Tanto tiempo, Roger.
Tanto tiempo, sí. Ese Isabel ya se fue a Suiza.
Sí, me moví rápido.
Ya se fastidió.
Ya me fui en el tubo, rápido. No, pues es que a veces como que quito el background y me siento rara sin el detector atrás.
Espérate que se encienda y quítate de allá porque ahí te van todos los
Sí,
haces.
exacto. Muy bien, Roger. Oye, ya se fue a Mario, ¿no? ¿Se fue Mario contigo?
Por aquí debe estar, no aquí en este momento porque la universidad está, no hay nadie, pero sí, aquí está contento.
Claro, porque es día festivo, ¿no?
Sí,
Sí,
sí
si
es
nos
festivo.
ponen a trabajar en días festivos. Mario Kawachi, ¿qué nos hace?
Este Mario, sí, no
Y
calculó.
desde las 8:30 de la mañana, desde las 8 de la mañana nos pone a trabajar hoy.
Me levanté a las 7 y me levanté a las 7 para poder estar aquí con ustedes.
Gracias.
No,
No,
bueno,
yo sí
pero
tenía
desde
que bañarme entonces a las 6.
no me bañé, pero después me bañé. Para venir acá sí me bañé. Pero
Bueno.
lo que sí me pasa es que en casa no tengo café.
¿No
Porque
tienes café?
sí tengo café, pero es soluble, entonces no me gusta mucho. Entonces sí tengo para tomar café. Aquí tengo todos los aditamentos. De hecho, los alumnos vienen y como tengo la moledora y todo eso, la tarde viene Mario. Mario también viene. ¿Puedo tomar café? Sí, ahí está. Son mis baristas por la tarde.
Se abre la cafetería de Roger en la oficina.
Ándale, casi.
¿De
Entras y
qué café
huele.
tomas?
Aquí hay uno que venden, uno muy bueno. Hay tres, ¿no? El de Veracruz, el de Oaxaca y el de Chiapas. Probamos la vez anterior, el de Veracruz y estaba bueno, pero un compañero que es de Oaxaca me dio un café que él cultiva. Y en esa segunda vuelta ya fuimos y compramos el de Oaxaca. Yo espero que la próxima sea el de Chiapas de Mario. Esperemos, porque sé que de Chiapas nos hace falta.
Sí, no, yo compro descafeinado.
También.
Sí, hay algunos. Dicen que hay unos descafeinados naturales que no usa tanto químico. Pero es que ya me siento muy sensible a la cafeína. La edad ya no me deja dormir.
Yo hacia allá voy seguramente. Pero por el momento, mientras pueda, me doy golpes de cafeína.
Hay gente que es muy susceptible a la cafeína, creo. Mi esposa, si toma con cafeína, luego no puede dormir, aunque lo tome en la mañana.
Ah,
En
¿sí?
cambio, puedo tomar café con cafeína en la noche y me voy a dormir. A mí no me hace.
Un café
No.
antes de dormir, ¿no, Francisco?
¿Eh?
Un café antes de dormir, ¿no?
Y claro, hielo, con hielo,
Sí, frito.
ya sabes. Ajá. Con hielo.
Sí, yo también soy de las que se toma algo con cafeína en la mañana, aunque sea en la mañana,
Exacto,
adiós sueño.
exacto. Mi esposa más bien dice, o sea, si toma un poco de cafeína, aunque sea en el desayuno, en la noche tiene problemas para dormir. Entonces tiene que tomarlo descafeinado.
Sí. Sí, no.
Eh,
Se nos fue la plática de café. Roberto, ¿tú presentas? Sí, ¿no? De Dark Matter,
Sí, soy el último, el que cierra.
el que
Yo
cierra.
supongo que al ser la última charla y que todo inicia a las 8:30 de la mañana, yo creo que
Ajá.
voy a dejar de perdido lo que quede, los que sobrevivan.
Todo hasta sí, oye, es que está pesado el programa.
Sí,
Me
todos los días
comentaba,
inicia a las 8:30.
me comentaba Mario que hubo muchas charlas y pues aceptaron, creo que casi todas. Entonces, el programa está bastante lleno y muy completo, muy bien. La verdad, la organización les ha costado para organizar a tanta gente y está perfecto el programa. Está muy bonito. Ahora sí que
Sí,
está muy bonito.
hay de todo. Eso
Sí,
me gustó también, sí.
sí, que aprovechen los estudiantes. No siempre hay talleres tan completos.
Roberto, ¿y tú ya has venido a México a este evento?
A este evento en particular creo que no. O sea, yo me acuerdo que hace tiempo estuve en Puebla para un workshop del CIFU, pero no recuerdo el nombre del evento. Yo creo que este workshop de partículas no es que lo hagan siempre en Puebla,
No siempre en Puebla, no.
va
No,
rotando.
cambia la sede, sí. Les contaba en la mañana a los chicos que, bueno, esto ya tiene más de 20 años, no me acuerdo cuántos años tiene, pues ya vamos para la 18ª. Pues yo iba como estudiante y se hace cada 2 años, porque un año es el taller y otro es el...
Claro.
La
Entonces
escuela.
tienen como 36 años, si es que lo han hecho cada 2 años.
Al menos, sí, a mí me tocó ir como estudiante y ahora no veo, a veces teníamos lectures, me parece.
Pero en la escuela, ¿no?
En la escuela, sí es cierto,
En la
workshop,
escuela,
sí, no me ubico. Sí, es cierto, sí. A veces, sí, en la escuela teníamos clases, que son muy buenos también para los estudiantes.
Sí,
Ujú.
es necesario ahí un poco de escuela.
Y sí, no, creo que estas iniciativas, no sé quién las haya empezado históricamente en México, pero creo que fueron muy acertadas, totalmente convenientes, acertadas para la comunidad y los estudiantes. Así que, muy bien. Roger, ¿tú dónde presentas? ¿A qué hora?
Yo voy a presentar un póster, pero el miércoles. Y no estaba planeado, pero de todas maneras dije, bueno, hay que presentar algo.
Ya muy forzado. Pero el miércoles, ¿no se presentan el jueves los pósters?
Ah, no
No,
sé.
el miércoles, sí, no el miércoles, perdón.
No
Sí.
me asustes. No me
No,
asustes.
miércoles.
Isabel.
Pero estás presencial, oye, bien.
No puedo. Es que como me hicieron el coordinador de aquí de la licenciatura, e hicieron ahora en la universidad todo un esquema de cambio de todo el plan de estudio, no sé qué.
Oye, esa burocracia que está.
Entonces yo dije, no, pues me inscribo y se acabó, ¿no? Mando a los estudiantes que deben estar por allá. Y dije, es todo bien. Pero la universidad me dijo, bueno, si estás allá y no sé qué, no sé cuánto, presenta algo. Y yo, está bien. Entonces ya me registré y listo. Pero no, yo sí estaba pensando ir, pero ya era demasiadas cosas aquí y no.
¿Y Francisco Larios, tú presentas?
Ahorita me toca hablar.
Ese sí. Es
El
el que
primero,
abre.
¿no?
Yo
¿Quién abre la...?
¿Eh? Ahorita me toca hablar. Yo de hecho, ya ni me yo ya tengo hace muchos años que que ya no asisto ni al taller ni a la escuela. Ahora me dedico a... Lo que pasa es que mi esposa y yo tardamos mucho en tener hijos y tengo hijos chicos, así como la ves.
Ah, no, pues te comprendo totalmente. Ah,
Pues es difícil viajar cuando ya tienen los hijos chicos, te anclas, o sea, es difícil viajar y la primera vez que fui, cuando recién había nacido mi hija y fui allá a León, Guanajuato, todavía estaba Arnulfo Cepeda, que ya ves falleció hace como 3 años, ¿no? Algo así. Y me habla en eso mi esposa de que la bebé se había caído de la cama y se había golpeado y no sé qué. Entonces siempre estás estando allá y siempre estás así como que te pones todo tenso, ¿no? De yo qué hago acá y allá mi hija se acaba de caer de la cama y se golpeó y no sé qué.
sí, no
Entonces,
digas, que sí. Sí, pero sabes que ahora en Brasil fue a una conferencia y
ajá,
ya desde hace como 3 años, porque tenía todavía a mi hijo más pequeño,
ajá,
promovieron esto de ofrecer el servicio de guardería. Y
ok,
este año, en la conferencia que fui, había servicio de guardería en la conferencia.
ok.
Y me parece muy acertado ese movimiento de servicio para papás o mamás, servicio de guardería. O sea, conseguir una guardería o un servicio. A veces hay hoteles cercanos que proveen este tipo de servicios, guardería. Porque es cierto que con hijos es como más difícil participar y eso así como que aumentas. Ahorita este evento está muy bien porque nos da la oportunidad de participar en línea, ¿no? De
Exacto.
hacer un poco híbrido. Porque aunque estés, por ejemplo, yo estoy en Puebla, aunque esté en Puebla, también tengo que dar clases, también tengo que unas reuniones. Por ejemplo, hoy fui en la mañana, pero después tuve una reunión y ya no me dio tiempo de regresar. Y entonces, pues ya ahorita que me puedo conectar, me conecto. Creo que fue muy asertivo, muy acertado el formato. Está muy conveniente.
Sí, sí. Sí, si no
Pero
hubiera en línea, no. eh, Igual Antonio está en una situación igual que yo, Antonio Bozas. Este, entonces, es difícil viajar, o sea, y luego ya también uno se cansa de viajar. Como que ya también dices tú, ay, quiero estar aquí
otra
en mi
vez.
casa. Sí, es cómodo estar aquí en tu casita también.
Sí, y además con esto que se abrió después de la pandemia, pues ya se abrió más el concepto, ¿no? Antes no se tenía tan abierto y ahora yo estaba quejando en las reuniones del CERN. Bueno, yo trabajo ya mucho tiempo con cosas en línea desde que empecé a colaborar en el CERN en el 2006. Habíamos usado Evo y luego Video y ahora Zoom. Y ahora me da risa que empiezan con este concepto de las reuniones híbridas. Yo, pero si nosotros siempre hemos sido híbridos, yo no entiendo que si ahora ya se inventaron copiar el término porque decimos híbrido, pero nosotros siempre hemos hecho las reuniones. Yo recuerdo que estaba tan ocupada que la reunión estaba en otro edificio en el CERN cuando era postdoc o cuando estaba en mi doctorado. Estaba en otro edificio en el CERN y solo porque, no sé, estaba así como no quiero perder ni un minuto de trabajo, no me iba al edificio, me conectaba desde mi oficina. Entonces, sí, esto de híbrido ya tiene como un poquito más de años, pero que ahorita ya el mundo ya vivió, ¿no? Ya lo está viviendo y que...
Obligaron,
Ujú,
nos obligaron, exacto.
así. Y como esto del coffee break deberían de abrir, deberíamos de abrir así como salitas, ¿no? Y ya como que nos vamos a las salitas en el coffee nosotros.
Claro,
Ya sé, está, según yo, son las 4:23.
Así es. Y me dijo Mario que sí están en el coffee break.
Ok.
O sea que
no falta que nos estén escuchando todos allá.
yo creo, me dijo a las 16:19 que estaba en el coffee break. Y yo creo que
El temor que yo
todavía
tenía,
están en.
yo no ponía la cámara porque tengo el temor de que aparezca en esa pantalla gigante mi cara y yo dije, ay no.
Pero no, mira, ya vienen, yo creo que ya vienen, ya
Ya podemos,
callarnos.
ya
Bueno,
silencio.
mucho gusto en saludar a todos. Bye bye.
Ya llegó Eleazar, cuidado, ya llegó Eleazar.
Ahí está.
Hola, Francisco.
Hola, sí, aquí estoy. ¿Se oye
Ah.
bien?
Perdón, creo que nos estamos demorando. Un minutito, ahorita ya comenzamos, ¿sí? Por favor.
Ok, aquí estamos.
No subiste tus presentaciones, ¿verdad?
No, no tenía que subirla, la tengo aquí en mi computadora. Espero que no haya conflicto
Sí,
por
está
eso.
bien, nos las compartes y a ver si después lo puedes subir o enviar de alguna manera.
Bueno, te lo puedo enviar por correo.
Sí, estaría bien. Dame un segundito, por favor.
Sí. Después de que haga la presentación, espero que no haya ningún contratiempo, te puedo mandar el PDF de la presentación.
Hola, Francisco.
Ajá, sí, aquí estamos.
¿Puedes compartir, por favor?
Sí. Ahí está, ¿verdad? A ver.
Sí, se ve muy bien ahí. Pantalla completa, si la puedes poner.
Ahí está. ¿Sí se ve bien?
Perfecto, ahí está bien. Gracias. Well, let us start with the next session. Now is the turn for Francisco Larios, who will present an electron-muon collider. What can be proved with it? Please, Francisco.
Okay, well, greetings, everyone. This is an electron-muon collider. What can be probed with it? This is in collaboration with Antonio Bozas, who gave a talk in the morning. So when we have an electron-muon collider, we don't have as much activity as in regular, electron-positron or proton-proton or proton-antiproton collider. So as far as standard models process is concerned, when we have two final state particles, really there is only one option, which is the elastic scattering. We can also have initial or final state radiation or a photon coming from the W line here. And that's about it. So there is not a lot of background in this type of collider. Now, when we think of 4 particles in the final state, then it gets pretty busy. It's almost just like a regular electron-positron collider. No, well, not quite, because we never have the muon-electron annihilation, of course. But here, for instance, we have heavy gauge boson production, which then they will decay into 2 particles or more. And so there's more activity. All these are examples of standard model processes. However, there is not a lot of background, so this kind of machine can be very interesting to probe anomalous signals or interactions, right? So what can be probed? Well, we have electroflavor violation, of course, but there have been other works in the past. For instance, like 22 years ago, they did the study of heavy neutrino production in this kind of machine. Then 7 years after that, in 2007, another work appeared on some sort of exotic neutrino, that this heavy neutrino that mixes with the light neutrino, so that you can have a 2-to-2 process with heavy gauge bosons. And then more recently, 2 years ago, by Bossi and Sciafalloni, they consider this process. You have lepton flavor variation violated by 2 units, it's mediated by a Z prime. Okay. And then last year, I ran into this article in which they actually make the case for the construction of this type of machine. Now that in the community, a lot is being discussed about constructing a muon collider. So it's always interesting to see if it would be possible to add these extra features to such collider that you can have electron-muon collisions. And they use 2 processes in particular. We obviously have, for instance, the electron-muon annihilation into Higgs boson that then decays to BDK. That's the search for an anomalous signal. But we could even have, as you can see the diagram below, the regular standard model production of a Higgs boson decaying into a BB bar. And this process, we could use it to probe the Higgs BB bar coupling in direct competition with LHC measurements. And what they find is that because of the cleanliness of the environment, the machine would be able to probe this coupling, which has nothing to do with flavor violation, right? They usually, in all these papers, they use 1 or 2 TeV center of mass energy. And we talk about luminosities of the order from 1/2 up to 2 attobarns that they say that it is feasible. So we decided to, do this analysis with all kinds of 2-to-2 processes with fermions on the final state, and also the case of 2 photons in the final state. And the idea here is, let's compare with measurements of low energy, the muon decay, or this muon nucleon interaction that gives rise to muon electron transition. This is not muon decay, this is a muon electron transition in the presence of a nucleon. Because they are very good in these 3 papers by Sasha Davidson and collaborators. They present very good, very stringent limits on dimension 6 and dimension 8 operators, 4 fermion operators, and even some operators with electric magnetic dipole transition magnetic dipole moments, and some dimension 8 E mu gamma gamma couplings. So the idea was to compare with the low energy measurements and see how well this machine could do. So we refer to the 4 fermion dimension 6 operators that are here in the well-known Warsaw basis of the standard model effective field theory, where you have, the different classes depending on the chiralities, right? For instance, the first 3 operators is all 3 left chiral SU2 doublets. And then you can have also 2 left doublets paired with 2 right-handed singlets, SU2 singlets. In the last column, what we're showing is the helicity amplitudes. So these calculations are very straightforward, very easy to do, and we get the cross sections are very, very simple. The cross sections end up being, because the amplitude squares end up being proportional to either ST or U, the Mandelstam variables. And for instance, the last option here of these four Fermi operators is when you have the four SU2 singlets that are right-handed chirality. So for instance, look at this process, this electron-muon colliding into electron-electron. If they both have, they both are right-handed chirality, that means that the anti-muon is left-handed helicity, right? So that means that if you're running the collider with a polarization of 100% right-handed helicity electrons and 100% left-handed helicity muons, then you open the window for this kind of interaction and you close the door for all the other helicity combinations, right? So for instance, here, we have the cross-section in such machine. For the case of the initial beam polarizations that I'm talking about, the coefficient of the operator that I showed to you appears here, but doesn't appear in the other possible polarizations of the initial beam, okay? We actually consider some dimension 8 couplings, 4 Fermi couplings of dimension 8 that were considered by Sasha Davidson in the low energy experiments. But what we found is that the bounds obtained there are like 5 or 6 orders of magnitude, not as stringent as the low energy measurements limits. So in this table, we show what kind of limits do we obtain. See here, like in this column here, this 4 times 10 to the minus 4 is the limit that is provided by Davidson that comes from the low energy measurements. And then in parentheses, what we have is the ratio of the low energy limits divided by the low energy limits from the collider that would be expected from the collider. So what we see is that the low energy limits would be always like a 2 orders or even 3 orders of, or even 4 orders of magnitude smaller. That means it's far more stringent. For the case of final states of second family, right, like muons or strange quarks or charm quarks, then the machine begins to have a what we would say competitive sensitivity, right? I mean, what happens is that in the 4 Fermion operators that enter the low energy measurement processes here, they usually enter through one extra loop, and so there is a suppression factor about 2 orders of magnitude in the low energy process, and that's why the measurement for the tree level production machine in the collider begins to becomes competitive. Same thing for the third family, fermions of the third family, right? Like tau leptons and bottom quarks. Okay. And actually, I'm getting to the end of my talk, which I did, I suppose, very fast because I don't want to run out of my time. We also analyzed the case of 2 photons in the final state. So those 2 photons can come either from a dimension 6. This is an electric, what we call a transition magnetic dipole term, or it can come from a dimension 8 electron muon gamma contact interaction, so to speak. And what we find is that actually the muon to electron gamma decay, the measurements of muon electron gamma are like many times more stringent than the limits that we can get from the collider. So nothing promising here, but for the dimension 8 coupling, the contact coupling here, we do obtain what we could call competitive couplings. As an aside comment, see, you would think that the limit coming for this process in the low measurements would probably come from muon decay into 2 photons, right? Well, it turns out that the best measurements, and I refer you back to one of the papers by Sasha Davidson, actually the low energy measurement that turns out to be very sensitive to this coupling is the muon electron conversion in the presence of nuclei. Okay, so for this case, we actually did the complete job of analyzing the background, the standard model backgrounds for this process. And since, again, this is a 2-to-2 process, that means that in the center of Maelstrom, those two photons have to be back to back. Whereas the standard model background involves always four state final particles, so that the two photons do not have necessarily to be back to back. It's not very difficult to set up some kinematic cuts that will separate greatly the signal from the background. And here, for instance, we show in the first row here, you can see in the last two columns, in principle, the cross sections for.
Francisco, 3 minutes left, please.
What is that?
3 minutes.
Okay. I'm almost at. This is pretty much the last slide. So bear with me. So I just want to see, the cross sections that we deal with the backgrounds in principle are like orders of magnitude much bigger. Once you start imposing the kinematic cuts, those backgrounds reduce dramatically, and that's why we get a very clean signal. So as a conclusion, in this machine, dimension 6 4-family couplings get very competitive bounds for second and third family final states. Dimension 6 muon electron dipole gamma couplings, the limits are weak compared to mu e gamma decay, but dimension 8 mu e gamma gamma limits are competitive with the low energy experimental bounds. And this type of machine could also probe couplings like Higgs BB bar that do not have anything to do with flavor violation, because of the cleanliness of the environment of the machine. And that's it. Thank you.
Thanks to be on time. Any questions in the room? There is no question. Maybe by Zoom, if there are any questions.
Hi, Professor. I have a question. These probes are into the standard model base or something, or is more than standard model?
What was the question?
These probes are in the standard model basis, or it's something else?
Are you talking about the effective operators, or are you talking about the production processes in the context of the standard model? Hello?
The production.
I having a hard time here listening to the sound is not good. I'm sorry.
I mean in the production process.
Yeah, the production processes again. See, for instance, these two photons. This is a standard model process. As I said, the processes that involve four particles in the final state. They take, that's where you get a lot of activity in the collider. But even so, to processes that are for anomalous processes that involve two particles in the final state, is very easy to impose kinematic cuts that will separate signal and background. I don't know, but I don't know what was the question about this. No, I'm sorry. Hello?
That's not the answer. Thank you.
No. Well, I didn't understand the question. I couldn't hear the question well. I didn't know what was the question in the first place. I'm sorry.
It's okay. Thank you,
Okay.
Francisco.
Okay, you're welcome.
And the next presentation is sorry. The next presentation is given by Fabiola Fortuna, which will talk about an effective dark matter standard model interaction with the spin-1 mediator. Please, go ahead.
Good afternoon, everyone. First, I want to thank the organizers for the opportunity to present my work here. My name is Fabiola Fortuna, and I'm going to talk about effective dark matter standard model interactions with spin-1 mediators. This is the outline of my talk. I'll start by a quick motivation, then I'll talk about the effective field theory that we use in this work, and then about the data that we use to restrict our parameter space. And then I'll show you our results. Okay, evidence for dark matter is abundant and compelling. I'm showing here just a few examples, as are the rotation curves of the galaxies, where there is a discrepancy between the velocities measured and the velocities calculated. Also from weak lensing, I'm showing here the visible matter distribution in the galaxy cluster Abell 1689 and the dark matter distribution in that galaxy cluster. And also we can obtain information about dark matter from the CMB anisotropies, where we see that dark matter accounts for almost 27% of the total energy distribution in the universe. Now, the effective field theory that we use, we were interested in dark matter standard model interaction with heavy mediators, and we focus on vector mediators. We can have in the dark sector scalars, fermions, and vectors, and we use phi for scalars, psi for fermions, and x for vectors. We assume the mediators are weakly coupled to both sectors, dark and standard, and also that the dark fields transform non-trivially under a dark group. And also we assume that all standard models are singlets under this dark group as a way to ensure the stability of the dark matter particle. Also, we assume all dark fields are singlets under the standard model gauge group. And the consequence of interactions generated by a mediator are that our operators have this form, with a part of the operators that contains only standard model fields, another part with dark fields only. In the effective Lagrangian, each term has factor 1 over lambda to the n, depending on the dimension of the operator. And as we assume that the dark fields transform non-trivially under the dark group, we know that O dark, this part, contains at least 2 fields. This is the Lagrangian that we use. In equation 2, we have terms with dark fermions, and in equation 3, terms with dark bosons, x for the vector and phi for the scalar. And this B here is the hypercharged field of the standard model that is a linear combination of the photon and the C boson. And these are our effective couplings. Now here I'm showing the same operators, but I'm introducing a new notation that we use in the following, that we will use in the following. The first 3 operators are the ones with dark fermions. And operators 4 and 5, the operators with dark bosons. Now, something important is that we use effective couplings, the effective couplings that correctly reproduce the observed relic abundance. That is, for each value of the mass of the dark particle, we fix the effective couplings such that they reproduce the observed relic abundance. And also, we analyze the combined contributions with the same dark matter candidate with the following relations between the lambda scales and the C coefficients. These relations in equation 6. Now, these are direct detection experiments. Currently, the most stringent limit on spin-independent scattering cross-sections of dark matter nucleon come from Lux Zeppelin. That is this line, this blue line. And I'm also showing data from Panda X 4-ton and Xenon 1-ton in these lines. And all the region excluded by these experiments, the region is the one above these lines. So you can see that all these operators are already rolled out by these experiments. In this mass region from 50 GeV to 1 TeV. So in the following, I will be showing just the operators that are not here. Limits from dwarf spheroidal satellite galaxies. These objects of the Milky Way are some of the most dark matter dominated objects known. And due to their proximity and high dark matter content, they're excellent targets for the indirect detection of dark matter. In this paper, they search for gamma ray. Well, they calculated limits based on data from the search of gamma ray emission coincided with the position of these galaxies. And there was no significant excesses of gamma ray emission. And they calculated limits on the velocity average dark matter annihilation cross-section. Here I'm showing an annihilation to BB bar in A in this plot, and annihilation to tau plus, tau minus. Again, the region excluded by the data is the one above the lines. So in this case, this data didn't help us to restrict our parameter space. And similar limits were computed by Ibarra and collaborators using measurements of the positron flux. So we have again limits on the velocity average dark matter annihilation into mu mass, mu minus, and electron positron. And again, these were our calculations fall below these lines, so are in the allowed region in both cases. Now, collider constraints. The effective operators we're working with allowed for the pair production of WIMPs in the proton-proton collisions at the LHC. If one of the incoming partons radiates a jet through initial state radiation, one can observe this process, proton-proton to dark matter, and the jet. And they will observe, or it will be observed, a single jet associated with missing transverse energy. And in this study, we include the Atlas monojet analysis based on 139 inverse femtobar of data from run 2. And I just quickly want to show some previous results that we obtained in an analysis for smaller masses. And just note that we had solutions for masses smaller than 2 GeV for these operators, and also in the region around 30, 40 GeV for some operators. Also, the ones without a solution in this mass range were restricted from direct detection experiments. And now the results from collider constraints. Oh, I didn't mention that we wanted to also test the results with collider constraints because these weren't, we didn't use collider constraints in this analysis. This is for operator 1, this operator. Again, our simulations should be below this data from Atlas. So this region of masses smaller than 2 GeV is no longer allowed. Neither is this. And here are the masses around 30, 40 GeVs. But we have solutions for masses larger than 1 TeV. This is operator, I can see what it, this operator 3. And also, these are no longer solutions. but we have some for masses larger than 1 TeV below the data points. For operator 4, we have some solutions in the region around 30 to 70 GeV, and also for masses larger than 600 GeV. This is for the combination of operators 1 and 2. And these also are no longer solutions. These are for masses smaller than 2 GeV. And finally, the combination of operators 1 and 3, where we have no longer solution for masses smaller than 2 GeV, neither for masses around 30, 40 GeV, but we have some for masses larger than 1 TeV. And this is a summary of our results. Just remember that the FFD couplings are the ones that correctly reproduce the relic abundance. The operators with non-solution are restricted from direct detection experiments, and the other stringent constraints came from collider constraints. And that's all. Thank you.
Thanks, Fabiola. Any questions?
In your standard model side where you have the B mu nu, you said that you have the photon and the Z boson. Can you distinguish which contribution is important in these results? Because sometimes can be driven by the Z, or in another parts can be driven by the photon. I don't know.
I will say that in the previous work for smaller masses, here, for example, we use the C invisible decay width to constrain the operators that have the possibility of the oscillating that particles. General, and sure, I use at the same contributions at the same time.
Another question.
What happens if you consider that the relic density that you produce is much smaller than the current density? Because it could happen that there are many contributions to dark matter, and then it is not necessary that all the relic density should be produced by this dark matter candidate.
Mm-hmm.
What happened with these bounds on the mass of the dark matter particle?
I will say that in general, we could have possible solutions because we use that, we impose to reproduce the observed relic abundance to test these operators, but I think there will be solutions for all, depending on the part that we will reproduce, I think.
Thank you, Fabiola. Another question? No. Thanks again, Fabiola.
Thank you.
The next presentation is with Luis F.L. Cerro, top quartz and vector meson production in heavy ion collisions at CMS. Please.
Yep. Thanks. Just let me check if this is working. Okay, so first of all, I would like to thank the organizer for this opportunity. My talk is on top quartz production in central collisions. and also vector meson production in ultraperipheral collision in LED data taken by the CMS experiment. So I will first talk about the top quark. So as we know, it was discovered in 1995 in Tevatron, and is the heaviest particle in the Standard Model, with a mass of roughly 173 GeVs, and it gives us a Yukawa coupling of nearly unity. So the decay time is very short. So the top quark decays before the ionization mechanisms. So basically, for the decay modes, we have two, depending on the decay mode of the W boson. It could go to leptons or QQ bar. And the top quark is primarily produced at a very high rate at the LHC by gluon fusion in TT-bar pairs. Here we have the Feynman diagrams corresponding to this. So basically, what we end up is with 3 decay channels for TT-bar. We have access to that at LHC. The first one is the semileptonic, in which one of the W goes leptonically and the other one goes to QQ bar or jet. Then we have the lepton channel, in which both W goes to leptons. And finally, we have the all jets or hadronic, in which both of the W goes to jets. And this is the dirtiest and more challenging channel to study TT-bar. And here we have a pie chart of the branching ratio, or the branching ratio contribution for each channel of the TT-bar decay. So since its discovery, TT-bar has been observed at CMS at the 4 energies available in proton-proton collisions. And also we have TT-bar in proton-ion, proton-lead collision at 8 TeVs. And the motivation to study TT-bar in proton-proton collision is that, first, the heavy ion side profit from this measurement, and also it is important because with TT-bar in proton-proton we can constrain the proton PDF, as we can see from this very nice QCD analysis, in which the cross-section of TT-bar is introduced, and we see an improvement for the gluon PDF relative uncertainty at high values of X, the Yorkin X. And the motivation to study TT-bar in the heavy ion side is first, we can prove nuclear PDFs with this measurement. And also it paves the way for using TOP to resolve the time structure of quark gluon plasma. As I will talk more about this later. So at CMS, we have the first evidence of TT-bar in nucleus-nucleus collision using LED data at 5 TeVs. This data was taken in 2018. And basically, we use the lepton channel because it is the cleanest, and we really appreciate this characteristic, especially in the messy environment of heavy ion. And to extract the cross section of this for this measurement, we used 2 methods. One is the lepton only, in which we only take into account final state kinematic properties alone. And we also take advantage of the B-jet identification algorithm we have in CMS. We have a theoretical prediction for this cross-section at next to leading order. And here we have a nice plot of a nice event, a candidate event for TT-bar in LED. Yeah, here we have just the BDT distributions for each one of the method we use. I just wanted to mention here that here, as we can expect, the Crow-Sim flavor is the highest, is the one with the highest sensitive final state. We see with the dilepton only method, we obtain a 3.8 standard deviation significance. And for the method in which we use beta-in techniques, we obtain 4 standard deviations. From the previous result, we can extract the cross sections, and they are both in agreement with theoretical predictions and also with PP scale data. And as we can see here, the statistical uncertainties dominate by far. In other words, we need run tree for observation for this. But anyway, this constitute the first evidence of top quark production in lead. We are making also some efforts to go further. Just this measurement, these dilepton measurements. For example, here we have an improvement for the TT-bar cross sections. We are recently published. Here on the left plot, we have the cross section calculated only using 2015 data, but we also improved this measurement by using the dilepton in the dilepton channel 2017 data. So we see that we are reaching even higher precision for this measurement, and this is good for the heavy ion side. We also have projections for TT-bar in the context of the high luminosity LHC. We can see here, well, this projection is focusing only on the dilepton only method, so no B tagging for this projection. But we can see here that assuming a 13 inverse nanobarns for high luminosity LHC, so far we have a 1.7. So assuming this, we obtain this very nice result, very precise result of TT-bar in lead. And it is worth to mention that the total uncertainty is expected to be half with respect to run 2. So we will push more for nuclear PDF determination from the theory side. As I mentioned, one of the motivations to study TT-bar is that we can resolve in principle the time structure of quark-gluon plasma. And I mentioned that the top quark doesn't hadronize in the case before hadronization. So unlike other jet quenching probes, which are produced simultaneously with a collision, TOPS can resolve the time evolution of the QGP because it is produced at very high energies. We have a Lorentz boost, a significant Lorentz boost. So depending on the PT of the TOPS, it can decay before or within quark-gluon plasma formation. So the idea here is construct like a movie, taking a snapshots at different times, at different PTs. So there are some phenomenological studies that make predictions about using TT-bar in the context of the heavy ion. For example, this one, in which they use the semi-leptonic TT-bar decay. So basically, we see here that in the context of high luminosity LHC, we have access to short time scenarios with lighter ions. For example, there is a prediction here for krypton. And with FCC or Future Collider, we will have access to the full time evolution of the QGP. So now I will switch the topic. I will talk about vector meson production. So in the context of TT-bar, for example, we are talking about central collisions. And yeah, heavy, in the context of central collisions, these kind of studies are mainly devoted to study quark-gluon plasma properties. For example, here we have the upsilon production in lead in central collisions. It was presented at Quark Matter this year. And for the first time, the upsilon 3S is clearly identified, and we see this very nice suppression here. But in ultraperipheral collisions, in contrast, the motivation to study this is that there is an interplay between QED, QCD, and beyond standard model physics for this. So as we know, ultraperipheral collision is there are collisions in which the impact parameter is greater than the sum of the two radii of the nuclei. And there is basically a photon-photon interaction there because of these large photon flux by this Weizsäcker theory. For example, see Mariola's talk this morning. Ultra-peripheral collisions are experimentally clean. Paradoxically, heavy ion collisions are the messiest and the cleanest. We can see from these plots on the lower part. So how do we produce upsilon, for example, in UPC? So here I have a Feynman diagram for this, in which a photon produced from one ion fluctuates to a QQ pair. And this fluctuation interacts with the other nucleus via two gluon color singlets. So we have a very clean signal in which we have a vector meson here, and the two initial ions. And the relevance to study this is that we can understand nuclear structure. For example, nuclear PDFs, especially at low X, for example, we have here the EPPS nuclear PDF, and if we go to lower values of the Bjorken X, we see that the uncertainty is very large. So we need a lot of work for nuclear PDF determination. And also we can constrain theoretical models with this kind of studies. So there are some CMS related analysis. For example, we have upsilon photoproduction in proton LED at 5 TeVs. Here we have the invariant mass, for example, and this the cross section as a function of the invariant mass of the photon and the proton. And we see what we see from here is that the spectral increase. We also have naive cycle prediction in the LED at 2 TeVs. Again, we have the invariant mass here and the cross section of as a function of rapidity. So vector meson photoproduction at CMS is being actively studied. And there are ongoing analysis, for example, JPSI and upsilon in LED at 5 TeVs. We just started finishing this analysis. The upsilon I am taking over this work from another collaborator. And this analysis in JPSI might bring new hints about saturation in nuclear behavior. This analysis will be published soon. And this brings me to my summary. In the top part side, we have TT bar at the 4 different energies at LIC in proton. And we also have TT bar in 3 different systems, and PP, PLED, and LED. We are looking forward for observation of TT bar in LED with RON3 data. And the top part in heavy ion is a unique proof to resolve the time evolution of the QGP. Yeah, you probably know that we started with RON3 already. Last week, we reported the first LED collisions. In the context of vector meson in UPC, it is important for nuclear PDF determination. They are relevant to understand saturation. And for quantum photoproduction analysis, there are some ongoing analysis in this context. And that's it. Thank you.
Question for Luis.
Hi, thank you so much for the nice talk. So I would like to ask you, what do you mean by saturation? And second question is, can you probe the transport coefficients of the quark gluon plasma with either with the vector or the TT production?
Yeah, for the first question was saturation. For example, here in this plot, if there are saturation effects we expect for these cross sections to reach a plateau, let's say, to be flat at high values of this invariant mass. Yeah, so here, these models, I think that they don't include saturation. This is why we observe an increase in cross section. For the transport coefficients, I'm not sure if we can determine with TT bar, but of course we have a determination, for example, of the shear viscosity in the CMS, and this is usually done with these azimuthal correlations, which we can extract the transport coefficient from those data.
Any other question?
I also like very much your talk. Sorry for the question, but can you go to slide 5?
Yeah.
There is something that I didn't see. Okay. So on the right-hand side, the computation of significance doesn't seem to be straightforward. Can you comment on the value that you get?
Yeah. For example, here in the 2 digits category, we only have 1 B. So this is a sign that we need more statistics on this.
Okay.
Yeah, I don't know if that is related to your question.
Yeah, my question is that 20 times 4 is 80.
24, sorry?
20 times 4 is 80, not 63. So it's not for, I mean, in the naive way to compute it, it's not for standard deviation. So are you doing something different or is just a typo?
Probably it's just a typo.
Okay.
Yeah.
So what is right, the standard deviations or the uncertainty?
I'm not sure. I have to check. Yeah, I don't remember on the top of my head right now. Sorry.
Any other question? Thanks, Luis. Thanks again.
Thanks.
The next talk is with David Francisco. We present phenomenological analysis in direct photon production using neural networks.
Hello, everybody. Thank you so much to be here. And thank you also to opportunity to present my work made in my master program at Universidad Autónoma de Sinaloa. This work is in collaboration with Roger Hernández Pinto, Germán Sforlini, and Pia Zurita. For this work, we are interested to study the direct photon and positive pion production in proton-proton collision. The principal goal to this is reconstructing the fractions moment carried by original partons in the collisions. We name H1 and H2, and the fraction moment transfer to the pion in the final state, where we calculate the cross-section next to leading order QCD plus leading order QED accuracy. This picture displays a general idea for this work, where H1 and H2 are colliding hadrons with linear momentum K1 and K2. the original partons interact, producing a photon measured in the final state, and this photon we name direct photon, and a parton A3 that is hadronized in a pion measured in the final state. This work is based to the work made for Daniel de Florian and Germán Sborlini in 2011, and the results for this work are published in the last year and this year. The hadronic cross-section is given by for the factorization theorem, what is the convolution between the PDF to find the hadron A inside the hadron H1, and the PDF to find the parton B inside the hadron H2, the fragmentation function to the parton C between that is generated between the interaction A and B is fragmenting into the hadron H. And the partonic cross-section, the parton A and B generate the parton C and the JH. Specifically, our cross-section, we add the isolation algorithm in the partonic cross-section. This is to eliminate other contribution where the photon in the final state is generated by other partons generated during the collisions. The channels that are considered for our calculate are shown in this table, where specifically this channel QQ bar to photon-photon is eliminated by this algorithm. The isolation algorithm consists in detecting a photon in the final state, draw a cone around it with radio R0. We define a smooth fusion that is proportionally to the transfer energy of the photon and a factor between 0 and 1. Also, we define the transfer energy inside the cone, like the energy, like the transfer energy inside the cone of the each partons in the cone. If transfer energy inside the cone is lower than the smooth fusion, so we say that the photon is isolated. So the photon we consider that is direct photon. It's not so the Monte Carlo simulation not consider this event. The codes used for this calculus are for the Phoenix experiment of Phoenix detector in RHIC experiment, but also we explored the LHC experiment. Here, like our first result, we study the distribution of the differential cross-section like a function of the fractions moments, where the red line is the leading order contribution, the black line, the next to leading order QCD contribution, blue line, we consider next to leading order QCD correction plus leading order QED correction. On here, we can see that there are a peak in that 3-5 and for RHIC energies, and other peak in C equal to that 25 for LHC energy. These peaks is because the cross section is calculated with with a convolution with the fragmentation function. There are important constrictions in this region. Other important result is that it exists a change of the spectrum where we study the fragmentation, we study the fractions moment of the edge, where we change the energy of center of mass. Now, there are leading order exactly solution and leading order correction, where this solution we can show like a function to the detector variables. This means transverse momentums, pseudo rapidities, and azimuthal angles. But when we consider the next to leading order accuracy or next to leading order correction, the solution for the fractions moment are not exactly. For the paper published in 2011, Daniel de Florian and Germán Sborlini shows the probability that reconstructing the fractions moment real, we consider fractions moment real, like they generate by the Monte Carlo simulation with this formula, where the black color is a best reconstruction. Black color is probability 1, while the white color is a probability 0. For this paper, we use machine learning techniques to calculate the fractions moment or approximate the fractions moment. Like we note the leading order solution are exactly, we made a test reconstructing the leading order solution of the fractions moment with this basis. And the results are a perfect reconstructions. But at next to leading order correction, it's not that easy to reconstruct in the fractions moment. For this, we use 3 different methods to reconstruct the fractions moment: a linear method, the Gaussian process, and the neural network. The linear method and Gaussian process is necessary to define basis to reconstructing the fractions moment. We define 3 different bases: general bases, bases inspired in leading order solution, and physically motivated bases. But to the neural network, we don't need define any basis. Only we need the measures in the detectors in training with this data, and the outputs. There are the fractions moment generated by the Monte Carlo. On here, we can see the results for the reconstructions for the fractions moment H, where the first line is the linear method, the second line, the Gaussian process. Here we can see that the linear method is better when we use general basis, but for each basis, the Gaussian process is better than the linear method. For the fraction moment C, we have similar result, but on here we can see the linear method is better than the last reconstruction, but the Gaussian process is continue better than the linear method. And where we made the reconstruction with a neural network to lead order prediction, we can see good results where this diagonal shows that this method have a bigger probability to reconstruct the fractions moment, but leading order prediction is a correction that we have exactly formula. The interesting here is when we consider reconstruct the fractions moment at next to leading order plus leading order QED correction. And here we can see the reconstructing is better than the Gaussian process and linear method. And also it's important to mention on here we cannot define any bases in the and only we need the valors directly take for the Monte Carlo. Okay, thank you. Finally, if we are the comparison between the machine learning methods with respect to the approximation formula at next to leading order, on here we can see that the machine learning method have better prediction when we use only the approximation formula. Conclusions. The linear method is better for general basis, but the Gaussian regression is better. The linear method has more flexibility. But the neural network offers the best balance between the assumptions and quality of the reconstruction. And thank you so much.
Questions, Father David?
Thank you, David. I found your talk very interesting. I wanted to ask you about the architecture of your neural network, the hyperparameters. Why did you choose to have 300 neurons? Also, why did you choose ReLO as your activation function and not, say, the sigmoid function, for example?
We can repeat again the other.
My first question is, why did you choose 300 neurons for your neural network?
Yeah. So, yeah. For the neural network, yeah, we use 5 hidden layers and 300 neurons per layers and a unitary linear rectifier like activation function. And these parameters are to test and error. We started with small parameters. Okay. And we use different tests. We change the try with different architectures to obtain the best architecture. Okay.
Thank you. And for the second question is, why did you choose the ReLO function? Why did you choose the ReLO function as your activation function?
Okay, yeah. Is the ReLO activation function is the identity, I don't know, identidad, where the edge is bigger to 0 and 0 for negative numbers. Okay, so R is a activation function.
Thank you. Thank you again. The next talk is given by Roberto. It will be online. Roberto, are you there?
Yes, I'm here. So can you stop sharing screen to share mine? Okay.
Can you share your slide?
Yes. Can you see my screen share?
Yes. Now it's okay. Please go ahead.
Okay. Hello, everybody. Thank you for letting me give this review on particle dark matters. I follow in this workshop since the morning, so it has been very interesting, all the topic that you have covered. So I'm gonna try to explain to all of you what is going on with dark matter in this context with the particle dark matter. So the plan of the talk is basically a brief introduction and to introduce what are the basic concepts around dark matter. To follow after that with explain a little bit about dark matter models and to finally with the conclusion. So let's start with the very basic. When we are thinking about dark matter, we must think about what is the standard model and what is around the standard model. We already know that, this image have been shown during the first day of the workshop many times. But after all, this is what is the state of the art, what we know about particle physics, the standard model of particle physics. And indeed, what is the most interesting part of the standard model is how it has been built in terms of symmetries, in which we already are very familiar with this Lorentz or the discrete symmetries like CPT. Also, the quark sector that is very well described using the strong interaction in terms of the SU3 gauge symmetry, and also the part with the leptons that mainly interact using SU2, the weak isospeed, and U1 hypercharge. After that, about the concept of symmetries that is behind the standard model, we already know that the matter content, either all the part of the particle that forms the stable object that we know, like the nuclei and the electrons as well, we can classify, or they are composed in 3 families of quarks and 3 families of leptons. And on top of that, we have all what is related with the spontaneous symmetry breaking of the electroweak symmetry that is related with the Higgs field that allow us to pass from the electroweak interaction, SU2 times U1, to the U1 electromagnetic, and then we can already are quite common with the electromagnetic force. And also, one of the particularities of the Higgs mechanism is that allow us to provide a mechanism in which all the standard model is mathematically consistent in a mechanism that allow us to give masses to all of these fundamental particles that form the standard model that we know. The standard model itself, since it's very successful model, also it has a observable consequence. We already already know that one of the weakness of the standard model is to impose, to have like consequence of all the symmetries is that the neutrinos are massless particles. We already know that this is not the case. We already know what, more or less the relation between the neutrino masses. Also, we have other symmetries or accidental symmetries like the baryon number conservation and the lepton number conservation. And with all of these, we can have all these stable objects in the universe. So this is the starting block in order that we want to explore new physics that is beyond the standard model and also allow us in some sense to explain also what is the nature of dark matter. So in that sense, talking about dark matter, we already know that dark matter is a very important part in current physics, especially because it's a very kind of simple hypothesis that is placed in the evolution of the universe that is supported by many types of observation at different scales. For instance, we're already quite familiar that dark matter is present as an extra gravitational potential in the case of dynamics of clusters and galaxies. So this is one of the ways how Vera Rubin realized that we need more matter in order to explain the radial velocities of galaxies. Also, we are quite confident that we need dark matter to explain how the structures are formed during the evolution of the universe since the early times. Also, the CMB, the cosmic microwave background and isotropies that are present, also they require some seeding that is thanks to the presence of the early bumpiness of the dark matter in the early universe. And of course, there are other observations of the baryoacoustic oscillation and many others that I haven't listed here in this part. So after all of this, one of the most important information that we can get from all the cosmological and dynamic and so on type of observation is the amount of dark matter that is present in the universe in the form of the relic abundance that has this value that is related with the cross-crossing different type of cosmological information, like the amount of the abundance of matter, the amount of dark energy. We are already quite confident that 26.8% of the energy budget of the universe is in a form of dark matter. We already don't know which type of dark matter is dark matter, but we already know that is there present. So if we think that dark matter is a particle, we need that dark matter has to fulfill some properties. First of all, since it's dark in the sense we don't know the origin, but we already know that it's a kind of transparent particle. It doesn't interact with the light. Furthermore, therefore, the dark matter must be electrically neutral or has a tiny amount of electric charge. This is all these conditions that I'm going to list that are with asterisks. Also, dark matter must be massive in the sense that to provide the gravitational pull for all the objects that we already listed before in the case of evidence supporting dark matter. Also has to be non-baryonic. It's not part of the nuclei hadron part of the particles. Doesn't interact with the color interaction with the struggle forces. Has to be stable as cosmological scales because it has to be present since the beginning, and has to be very weakly interacting in the sense that the interaction with the rest of the matter that we already know, the standard model, has to be very small. Otherwise, dark matter would affect all the structure formation, and we wouldn't be able to conceive both scenarios. So if we are thinking from the dark matter point of view, we have to think in the context of the cosmological origin of dark matter. So in that sense, if we have the history of the universe since the beginning till today that we are here, if we want to know how dark matter is formed, we need to focus in the early universe. That part of the early universe is going to allow us to understand how the dark matter abundance is formed and how dark matter, therefore, after the CMB, CMB formation, continue to evolve, allowing the formation of structure and the formation of the Milky Way and we inside the Milky Way and so on and so forth. But from the point of view of particle physics, this is the very interesting part that we are going to try to, I'm going to try to explain you now. So if we are interested in the formation of the dark matter abundance, we need to rely on explaining how the universe evolved like a whole. That means we have to understand how is the metric of the universe. In this case, is the Friedmann-Lemaitre Robinson-Walker metric. And following the rules of the general relativity and thermodynamics, we can have a description, a pretty good description of how the populations, the different type of particles that are inside the universe, evolve during the period in which the universe expands or suffer period of reheating or cooling down, so on and so forth. So just an example, we need to deal with the Friedmann equation to know how the expansion rate of the universe is changing, yeah, in terms of the type of content that is in the universe. And if we are focused more related to how the population of particles that look like their matter will evolve, we need to deal with the so-called Boltzmann equation with source terms, in the sense that we have a part in which the dark matter will follow the flow of the expansion rate of the universe, but also we have to describe the part in which the dark matter has to interact with the rest of the population, in this sense, the standard model particles. So if we try to focus even more in the Boltzmann equation that describe, just in this case, the population of dark matter particles in the universe, as I said before, the first part, the left side of the equation, is related just how the population evolved in the space-time via the Liouville operator, but in this case, it's just a term that depends on the Hubble constant and how the time evolves during the period of the evolution of the universe. So in this part, the Hubble constant here, we can take in the standard scenario, the Hubble constant that we already know, but also opens the door to explore what happened in the case of non-standard cosmology, in which the Hubble constant has different contribution for other species that we are not aware that exists. And from the right-hand side of the equation, we have the part that is related with interaction. This is a simplified version because the collision term could be much bigger, the expression. But in general terms, we can find different parts. One part that is related with interaction between the dark matter particles and the rest of the universe, standard model particles that usually they are in thermal equilibrium. And of course, this interaction rate will affect how these two populations differentiate in number density. So I'm speaking very fast in this case, this equation naturally tends that the population of dark matter particles and the population of particles that are in equilibrium, the standard model, they try to be a match. So it has the same value. So the dark matter particle tends to be in thermal equilibrium with the particles of the early soup of standard model particles, but only when the expansion rate becomes so big, because here we are gonna have to compare the cross section with the Hubble expansion. When this term becomes negligible, we observe the one process that is the thermal decoupling, that is also known like freeze-out. That is a type of case that is very well studied, that is very academic, also to explain in lectures of thermodynamics or other type of mechanical statistics, that is related with how we describe the WIMPs, dark matter particles, or how the neutrino decouples also as later stages in the universe. Also, depending of the size of the interaction, we can have another type of process in which also other type of dark matter particles could be produced as the result of the early universe. That is a mechanism called freezing or FIMS for the dark matter particles that appear in this scenario, in which the dark matter cannot reach thermal equilibrium with the standard model particles, but therefore they decouple at the right moment to have the relic abundance according to the observations. So in that sense, I'm gonna focus only in the WIMP dark matter scenario. The same equation that I presented before is basically here described by, this is the curve for the equilibrium particles, and this is the case for the decoupling that happens depending of the size of the annihilation cross section. What is the information that we can get from studying the evolution of the formation of this dark matter abundance is that for the case of WIMPs, we have that the WIMPs are going to be Big Bang thermal relics because they were in thermal equilibrium with the early soup of standard model particles. That means that the relic abundance comes from this thermal decoupling, the freeze-out mechanism. And also, if we want to explain the dark matter abundance that we observe in the universe, we need that the mass range of the dark matter particle should be in the GeV-TeV range. That means it's a good indication, or it's a good mass range, if we are thinking in collider experiment or observatories of cosmic ray, gamma rays, or even neutrinos. So we are in the kind of in the good spot to observe this type of particles because of the mass. But above that, the fact that dark matter, at least in the case of WIMPs, was in thermal equilibrium in the early stages of the early universe, that means that it has to have a certain amount of cross-section with the standard model particles. Typically is this value, but depending on the analysis, could be a little bit smaller or a little bit higher because this is just a vanilla scenario. But at this point allow us to develop different type of dark matter search strategies, because since the dark matter was in thermal equilibrium, that means has an interaction with the standard model particles. That means that nowadays this type of interaction must be existed because the relic abundance is one of the big numbers that we want to reproduce if we are going to test different type of dark matter models. So in this sense, because of the relic abundance, we already know that in the case of WIMP, we can have indirect detection, that is just annihilation of dark matter in galactic halos of dark matter, direct detection, that is the scattering of between dark matter particles and nuclei in, for instance, xenon and crystals or sodium iodine, astrophysical probes. In the case when you have overdensity of dark matter, maybe dark matter will interact with itself. And of course, in an indirect way, but not indirect way like indirect detection, but in a different way, we can produce particles related with dark matter in the case of theories beyond the standard models. So we have already many type of experiments and observatories that are dealing with this type of observation. We have Fermilab for the gamma rays in order to see, besides other observables related with astrophysics, to see for signals of dark matter. The Planck satellite measuring all the part of the CMB and isotropies and see what is the role of dark matter at that point. Xenon 1 ton looking for the scattering between dark matter and nuclei, LHC of course, and the Palette cluster like a test to see how much is the interaction between dark matter and dark matter. So if we have many type of indirect searches, as I said before, but we are very interested to see what is happening in the future. We have already the ones that are running, like Fermi, MAGIC, HESS, LASSO in the case of gamma rays, but also we're expecting new experiments with better sensitivities and with larger range of energy if we wanted to see if dark matter maybe is heavier than the typical WIMP scenario. So in that case, we have CTA, like a Cherenkov telescope array, and this WGO, depending where it's going to be located, but it's a water tank similar to HAWC. Also, we have different experiments and field experiment with direct detection. And all of these indicate that at least for the case of WIMP dark matter, we are arriving to a place in which we are starting to explore all the possible corners for this type of dark matter candidates. So if we want to try to explain the nature of dark matter, we need to try to address extension of the standard model. In the sense, we already know that the standard model is a good model, explain many type of observation. And therefore, if we want to include a dark sector to explain part of dark matter, maybe we have to include it in such a way that is compatible with the symmetries that the standard model already have. So in that sense, usually the simplest way to expand the standard model is to the standard model Lagrangian to add the beyond the standard model fields and interaction. In that sense, sometimes we have to, usually most of the time, on top of the symmetries of the standard model, we add extra symmetries. For instance, to stabilize the dark matter or other type of, or to give flavor symmetries to the model, etc. So in that sense, this is the most common scenario, but it's not always the case. In this scenario, I'm gonna just present different examples of standard model extensions. So one of the models that is very interesting in the way that how it was constructed is the minimal dark matter scenario. In that sense, usually, as I said before, the standard model gauge group or symmetries of the standard model usually are extended in order to encompass dark matter, or maybe to explain flavors, symmetries, or neutrino masses, okay? But in the case of the minimal dark matter, it was just to ask the question, which type of fields I could add to the standard model without adding any extra symmetry, only using isospin, SU2, and U1 hypercharge for these extra fields. So it's just a construction of a model in terms of how we can, just by the structure of these two groups, provide some a scenario in which we have a good dark matter candidate. So in that sense, for instance, if we want to add a fermion, is to ask the question which type of representation of SU2 and with which hypercharge is going to produce a dark matter candidate, and the same would happen with the scalar scenario in which for this minimal dark matter model. So analyzing all the possible combinations of fields, fermion and scalar in this case, the only two type of structures that we can add in this scenario would be, if it is a fermion, is a quintuplet. In that sense, we are safe to not have any decay rate so to have an unstable dark matter. And in the case of a scalar, it's a septuplet. So in this scenario, we have a dark matter candidate. Doesn't mean that it's the dark matter of the universe, but the dark matter candidate that is constructed just using the standard model symmetries and not adding extra symmetry. Okay, besides the case of the minimal dark matter case, we have what happens if we try to answer two questions at the same time, or to try to solve two problems at the same time. One is the neutrino mass, how the neutrino get the mass that they have, and also it's the dark matter. So a brief introduction about neutrino mass mechanism. In the standard model, we can give masses to neutrino via the Weinberg operator, but the problem that it is dimension 5, so that means that it breaking some renormalizability properties of the old gauge structure of the standard model. But it's a good operator because it doesn't break any symmetry of the standard model. It's already SU3 times SU2 and U1 invariant, this operator. The only point that in order to include it in the standard model, besides that is dimension 5, is that we have to break lepton number into units. That is one of the first implications that has the standard model as it is now. That is the lepton number is an accidental symmetry, and this is related with if the neutrino has mass or not. So in the case that we already know the neutrinos are massive, lepton number must not be a symmetry of the nature, or at least not a symmetry that is actually working on our energy scale. So in that sense, when we open the Pandora box of the Weinberg operator, we can have different mechanisms to give mass to neutrino. The typical ones are the known like seesaw mechanism. We have different construction in which we need to extend the standard model with new particles. In the case of the type 1 seesaw, the neutrino right-handed. Type 2 is a scalar triplet, and the type 3 is a SU2 triplet fermion. In all these cases, we are going to get massive neutrinos. But the question is, how we can do in the case of dark matter? Can we provide some type of candidate in these scenarios? So depending how we address the problem of the neutrino masses, we can deal or not with this answer. So one case that is the kind of simple approach to deal with the neutrino masses is assume that the lepton number, it is a symmetry of the model, but it's just spontaneously broken via Higgs mechanism or similar Higgs mechanism. And therefore, we are going to have a Nambu-Goldstone boson. But in some sense, if we want that this Nambu-Goldstone boson to be a dark matter candidate, we need to be it has to be a pseudo Nambu-Glos, so it has to be extra ingredients in order to provide this. But the Majoron model is a kind of action-like particle. It's going to try to address the problem of neutrino masses in terms of the BEV of the triplet, or the doublet, or the singlet. That is the 3-to-1 model. But even though this Majoron is kind of effective model to try to deal with the part of the dark matter, it's a good candidate because we're going to produce masses in the order of the keV for this kind of dark matter candidate that is the Majoron. Of course, one way to observe Majorons is via the decay into photons or into neutrinos, but neutrinos are harder to see, so it's better to observe like photons in the range of the keV or mega electron volt that is in the X-ray range. So beyond the mechanism that occurs at tree level, with, for instance, with the seesaw, is the case of the radiative seesaw. Radiative seesaw try to deal the problem of the neutrino masses, just that neutrino masses are smaller because it's not a process happening at tree level. It is a process happening at one loop or larger loop. So in that sense, the radiative seesaw is trying to produce the Weimer operator, but instead of produce it by tree-level processes, it's just one loop. What is the nice way, or the nice properties of radiative seesaw is that because the loop has to be protected somehow in order to be the leading term in the neutrino masses, this allows us to introduce a dark symmetry or a symmetry that is protecting the loop to generate the neutrino masses. But as a bonus point of this construction, particles that are inside the loop could be the all dark matter candidate. So in that sense, the lightest of the particles that are inside the loop, and is also electrically neutral and satisfy the other properties that I said in the beginning, is going to be a particle that is fully stable because that this dark symmetry is present and it's exact and it's not broken. Otherwise, if it is dark symmetry doesn't exist, the neutrino could get masses via a tree-level process. So in order to protect the loop, we have neutrino masses, but as a plus, we could have dark matter as a result. So in this scenario of radiative seesaw, there are some class of models that are very known, that is known as scotogenic model. Their basis basically is the realization of the seesaw type 1, but at one loop, so adding a right-handed neutrino and a scalar doublet. Type 3, that is similar to the case of the type 3 seesaw, in which we add in the same SU2 triplet fermion and the scalar SU2. In both cases, there is a Z2 symmetry that protects the loop. And in both of these two cases, we get the different type of dark matter candidate, either the right-handed neutrino that is here in the as a fermion singlet, or the neutral part of the scalar doublet, either the real or the pseudo-scalar. The same in the case of the type 3. We have the neutral component of the triplet and the two scalar and pseudo-scalar coming from the eta field. So if we want to analyze the parameter space of this model, they are quite well studied. But we can find that, for instance, in the case of the type 1 scotogenic model, if we want to explain the full amount of dark matter, I mean, all the relic abundance is coming from the dark matter candidate provided in this model, we have that we start to more or less 500 GeV to larger value of masses in the case of the scalar dark matter scenario. Of course, this is going to have some implication in the case of searches, indirect searches. In the case, this is the line for the full dark matter relic abundance. And good prospect because maybe CTA is going to be able to find or to observe the gamma rays produced in this type of scenario. Okay, so beyond the type 1 and type 2, type 3, sorry, this is a model, and this is a model that we proposed with Matthias Pierre. This is the scenario in which we are trying to construct a scotogenic model similar to the type 2 with the fields of the type 2. So in the fields of the type 2, we have the delta and the lepton doublet, but in this case, since there is the dark symmetry, it cannot be a lepton doublet. But the structure in order the minimal construction of this model implies to have two scalar triplets, one with and without hypercharge, and a vector like SU2 fermion. This is nice because the mass range of the fermion is not constrained by the Higgs mechanism because it's a vector like fermion. And of course, this is going to have a better interplay than in the case of the previous scotogenic scenarios, scotogenic model. So in that sense, in this scenario, as I said before, we have the two scalar triplet and two vector-like fermions, and the scalar field coming from the combination of the neutral part of the delta and the omega is going to be our dark matter candidate. There is no other dark matter candidate. It's going to be only the real scalar in this scenario. So, as we can do with all the other models before, just I wanted to fix in this example, we can calculate the neutrino mass matrix, and furthermore to get the eigenvalues and see what are the values of the neutrinos, and reproduce what is the mass square difference between the different eigenstates. Also, the mixing angles between the gauge states and the mass eigenstate from the neutrinos, in order to encompass and reproduce all the observation, the global fit for the neutrino oscillation parameters. So in that sense, it's just to show that it's possible to reproduce this kind of observation. But in the sense of what are the signature of the dark matter itself, because let's say for this scenario, neutrinos is like most a constraint for the model rather than a observational consequence of the dark matter, because of all the particles that are inside the loop right here. So in that sense, if we want to study what is the different indirect searches scenario, we have to deal with many type of annihilation channels. So all the possible combination of standard model particles that are produced due to the different annihilation cases for this dark matter. And usually this part, most of the people deals with using MATGRAPH or PYTHIA, and also micro omegas for the calculation of the radial abundance. There are many software available in order to deal with this type of construction, because by doing it by hand could be too hard to compute without any help of some type of software. So in that sense, if we analyze this type of indirect searches in this scenario in particular, we observe that we are going to get some signature for the annihilation cross-section of dark matter going to W plus W minus in terms of the mass of the dark matter. And we can observe that many points that are related with direct detection also constraints, if we are close to on top of the level of xenon 1 ton, or in the reach for the future Darwin experiment, or above or below the neutrino floor, we can see that for the point of view of the emission of gamma rays coming from the annihilation of dark matter into Ws, we are going to be in the ballpark to observe the CTA would be able to start to explore this type of models. What is one of the features of this model that, for instance, the other case of the scotogenic in the type 1 case doesn't provide, is the part that we can deal with heavier dark matter particles, TeV dark matter particles. This is not common in the case of general WIMP scenarios. Only this one, and for instance, minimal dark matter, they have the tendency to have heavier dark matter particles, because the dark matter particles are coming from higher representation of SU2, triplet, quintuplet, or septuplet in the case of the minimal dark matter. This is going to be a signature that is going to be associated to heavier and heavier dark matter cases. Okay, if we analyze the tau channel, we are going to be very happy to be explore this model in the case of CTA. This is a particular about this model but as I said before, we are going to explore ranges beyond the TeV, 2 TeV or 3 TeV, depending of the scan, on how heavy is the scan to perform. But in any case, beside the indirect searches in gamma rays, also there are indirect searches in neutrino. This is depending of the construction of the model. It's going to be a signature or not a signature of the different possible construction that can be done by only extending the standard model. Here I haven't talked about, for instance, supersymmetry, another type of model that are include much more number of fields. But in this case, it's very important to realize this type of effect, that depending on the extension is the type of signature that we can have, and maybe be able to have some possible studies in different type of indirect detection experiment. In the case of direct detection, also since our dark matter scenario is a dark matter that interacts via the Z and W boson because of the SU2 part of this construction, the signatures in direct detection is going to be in the ballpark of the experiment. This is in part because we have. This is in part because of the particular construction of the model. As I said before, we have part that is related with the Higgs portal because of the construction in the case of because also it is a scalar dark matter case, and also we have also contribution because of loops if we are just calculating the contribution with the interaction with the quarks. So this is arriving to the end of my talk and the conclusion, because particle dark matter is very extended scenario. I mean, there are thousands of different type of extension that we can put only on top of the standard model, and these construction are going to be very easy to try to filter using observables. Like for instance, the strongest observable to filter a model is the relic abundance. So no matter the type of the dark matter candidate that we are provided with the extension, if it is not capable to fulfill the dark matter abundance constraint, is going to be very hard to push it further in the analysis. But anyway, in this case, just trying to provide a dark matter candidate is a very interesting way how to extend the standard model, because we have to think the possible extension and which symmetries maybe are going to be related. Also, the connection with the different standard model puzzles. In this case, I talk about neutrino masses, but could be also flavor symmetries or lepton-flavor violation processes, or for instance, contribution to the G-2 of the muon. Also, there are many ways to motivate how the possible dark matter or the dark sector is related with the standard model sector. And of course, I didn't have the time to explain with all the details, but not only WIMPs are very well motivated candidates. Of course, actions and sterile neutrinos, they have the very, very important roles, and maybe those could be also the dark matter that is present in the nature. So this is all for my talk. Thank you very much for listening.
Thanks for the great review. Are there any questions?
Thanks for your talk. I can think about another standard model puzzle that is related with this pseudonumber Goldstein boson, no?
Yes.
Is it related with this accidental symmetry, no? The lepton number. Yeah. It is any kind of relation with this problem or hierarchy in the related with the leptons? Because I remember a paper that is related with this spontaneous break symmetry break.
Yeah, I mean, in some sense, the naive hierarchy that the Majoron tried to answer is because why the neutrino they have this tiny mass, okay, just to separate with the charged leptons. But in general, to explain the hierarchy problem within this lepton sector, the Majoron is not aimed for that. It's just aiming for the neutrino masses. Of course, as I said, this type of minimal model is just assuming that the lepton number is the symmetry of the nature and is spontaneously broken, but it doesn't forbid to have other type of symmetries that is related with the lepton and maybe with the baryon number. So that sense could be, you can put more pepper to the different type of symmetries of your model in order to try to explain the different type of mass relation between leptons.
Okay, thank you.
So, hi, thank you. This is more a sociology question that perhaps has a physical motivation. In many of the dark matter studies, they use as a bench point mark the Cherenkov telescope array, which doesn't exist. On the other hand, HAWC already exists and has data. Do you know
Yes.
what is?
I didn't listen the last part, the question.
Why people doesn't use HAWC as a parameter, as a benchmark? For instance, in this plot, CTA doesn't exist, so we don't have data from the Cherenkov telescope array already.
Yes, yeah. In this case in particular, is because if I remember well, because it could be the memory. I remember that HAWC is maybe over here in the level of, or maybe higher. Sorry, because HAWC tend to be larger than TV. So in that sense, for this model, it was kind of stretching the HAWC because HAWC is very important. And later also with the upgrades and accumulating statistics, maybe it's better than CTA, that is just a telescope that has to point to the different sources. Meanwhile, HAWC is gonna be more larger aperture in that sense. But yeah, here for this analysis in particular, just to avoid just like a reference, we put HES, like a example of points that are already ruled out by in this case a gamma ray observatory. Yeah, but I know what you remember. What are you meaning with the do not put the HAWC? It's just maybe for I don't know.
One more question.
Thank you. So my question is very fundamental. So what is your motivation or justification for thinking that dark matter is a particle and not a modification to gravity, or both? So what is why do you consider that dark matter is a particle?
This is it's not at the end the nature is gonna decide which type of answer is gonna be what is dark matter, but in the sense of technical, in let's say that is the argument is that first of all the dark matter is kind of the Occam razor, let's say, is a simple hypothesis. It's just a type of matter that is gravitationally bound to the objects, and the only point that is not interacting with light. So this is the reason why we don't see it. But it's a very simple hypothesis, and this hypothesis that have been have been backed up by different observations. It's not that we know what is the origin and the type of dark matter that is present, but we already know that, let's say, this hypothesis is, the dynamic of cluster or the CMB anisotropies likes this type of hypothesis, like a test. Of course, could be also the possibility that if there are modification of gravity that can reproduce the same observation, it's going to be as valid as the hypothesis of dark matter. And now that this dark matter is a particle, I guess this is only because we already know that the standard model of particles, of particle physics, is not fully constructed, because we already have some evidence of at the level of standard model that there are some issues with it that is not fully explained by the dark matter by the standard model itself. I mean, we already know the standard model is the greatest model in particle physics for explaining maybe 99.999 of the observation that we have done. I mean, in some sense, the standard model was built using all this observation of the different experiments of particle accelerators. But there are some issues with it that indicates, I mean, let's say that we are not talking about dark matter or dark energy. We have some issues with it that we would like to have answered. We already know that the standard model is not complete. Maybe dark matter is part of the puzzle that has to be included in the final version of the standard model. But it's okay. It's kind of philosophical or maybe sociological answer to the question. But in that sense, it's try to deal with these two problems. Standard model is not fully complete, and for the other side, dark matter is a nice hypothesis that manifests in different type of cosmological or gravitational observables, like the dynamics and so on. But I'm not saying that maybe later on we start to get observation with for instance, with the gravitational waves, that really the standard, the general relativity is not the latest or the last explanation for gravity and required to be modified, and in order to encompass the new theory of relativity or general relativity, we will get some phenomena that is better to explain in all the stuff that we are trying to explain with dark matter.
There is one more question.
Could you come back to your, I think, minimal dark matter model, the one with the 5-plate and septuplet? Okay, so just before, yeah, no, the Lagrangian. So for the fermion, is it vector-like?
Yeah, I guess yes. I mean, yeah, I have to be vector-like because of order to try to, just by the SU2 structure, to not be coupled somehow with the standard model fields.
But for the,
and also to deal with the mass of the dark matter. No. It has to be some mix, I would say.
Okay, we can talk later details. Thank you.
Yeah, I would say that because you have relative correction of the masses in order to make the split between the neutral and the charged part. And in fact, now that you said that, that you remind me that this is one of the, I mean, nice or not so nice properties of the minimal dark matter, that because if a very rigid structure of quintuplet or septuplet, your mass range for your dark matter particle are very narrow. So for instance, for the quintuplet, you are around, I just 10 TeV, let's say, I don't know, I put the 10 TeV in the 10 TeV range, and you cannot go higher or lower because all the annihilations in the universe, because of the W's and Z's, is just restricting that when you have this value of mass, you have the relic abundance. So I guess, if I remember well, even though it's a vector-like, you can generate a small mass splitting between the neutral and the charged part because of the relative correction with the Z boson and photons, making them heavier and your lightest state to be dark matter, but they are all very close in mass.
Thanks. Here is the last question.
Thank you for your very nice talk. Could you explain how is the dark matter abundance in the early universe in the case of FIMS?
Yeah, in the case of FIMS, let's say that, okay, I'm gonna erase this to, I'm gonna move okay. In the case of FIMS, let's say that this is the simplified term, because we can add other terms related with with decays and so on. So let's assume that for the moment we are gonna ignore this. In the case of films, we have a freezing scenario. So that means that our annihilation cross-section, let's say, has to be very small, because if it is large enough, our dark matter will reach thermal equilibrium very fast. So we want to make it slow, this part. So not thermal equilibrium of the dark matter, but has to be, in some sense, the good amount of cross-section of interaction in order to start to populate the amount of dark matter and in the right moment to decouple. So let's say that is a earliest stage of a freezing, and when it's in the right moment of the correct relic abundance, or dark matter particle is going to freeze out at this point. So that means if we take the graph that I have here, let's say that the freezing scenario, you start with 0 dark matter, and because of the small interaction rate, little by little, it started to populate the amount of dark matter in the universe. But the point is, just in the right moment, when, let's say, reach the value of the freeze out, the value of the relic abundance that we need, it's already the universe too cold and freeze out from the population. So in that sense, the freezing is because it started to, well, let's say, I know that I'm not English is native English, so for me it's like you start very cold and start to warm up a little bit. I mean, the population start to increase because of the small thermal interaction with the standard model particles, and just in the right moment when the standard model, the dark matter start to kind of reach thermal equilibrium with the universe, already decoupled, and then producing the relic abundance that is what we need to fulfill in order to explain structure formation and all the stuff that happens afterwards in the evolution of the universe. But this is this is the parameter that fixes everything. If it is too large, it's freeze out. If it is too small, small in the right amount, your dark matter candidate is gonna freeze in, like a formation of the relic abundance, of course.
Okay, thank you very much.
Mm-hmm.
There are one more question by Zoom. Please, who is in the Zoom? Can you open your microphone and ask?
Yes, hello.
Hello.
Can you hear me?
Yes.
I have a question in this. First, the minimal symmetry that you showed in, well, for example, is the majoron. These particles are also WIMPs or are another kind of particles?
No, in this case, the majoron, even though all of the candidates are WIMPs in this talk, the majoron is the only one that is not WIMP, because first of all, the way how we interact with the particle standard model is closer to a FIMP, because the only way that, for instance, in the majoron that only has the singlet part coupled with the standard model is going to be via neutrinos. So it's not going to be very, very strong, very intense, the interaction with the standard model particles. And the other part of the other feature that has the majoron as a dark matter candidate is it is a decaying dark matter candidate, in the sense that the only way that the majoron can make signals is via the decay of itself into neutrinos or photons, via loops, to these two type of particles. This implies that the mass of the majoron has to be in the order of the keV in order to be cosmologically stable, but also to not be so bright and to be already observed in the X-ray searches and so on. So let's say that majoron is the only case here in this talk that is not WIMP, is closer to a FIMP in that scenario, in this case. But has to be very light, because if it's heavier, it would decay too fast and you don't have any more dark matter in the universe.
Okay, then its relic density is related with FIMPs and not with WIMPs.
Yes,
no?
Exactly.
The process, the freezing in
Yes.
this case. Yeah, and my other question is, if we you say that the energy scale of these dark matter particles are in GeV and TeV. Okay, so and we can produce these kind of experiments, but why we have not found it until now, for example? That doesn't mean that there is a problem in this, or not even.
You mean? Do you mean kind of in the minimal dark matter case?
Yes, for
Or
example.
in general?
Or in general.
Yeah, here I guess if to produce you mean in colliders, there are some kind of bounds for different accelerators. For instance, in this case, to produce because this let's say that for the point of view of any collider, dark matter and the partners of dark matter, let's say the charged parts of the quintuplet or septuplet, they're gonna be in the ballpark called like electrowickinos. And in that sense, to produce 10 TeV particles, they are two out the reach of the LHC, at least in the what is shown here. So that means that even though it's heavier, the dark matter is not in the reach of the terrestrial experiment. But it's not the case of indirect detection, because cosmic rays or gamma rays can be in the reach of 10 TeV. I mean, the future observables and the current observable, for instance, HAWK or maybe SWGO, also CTA, they are aiming to observe gamma rays going to the heavier part of the gamma ray spectrum in the TeV. So one of the ideas, in part, to study astrophysical sources, but also to see what is happening with this type of gamma ray produced, for instance, for the annihilation of dark matter or for decay of dark matter. I mean, these are WIMPs, but to have an observatory that can see gamma rays in the TeV allow us to see either WIMP in the case of annihilation, but also could see other type of dark matter models that have decay in dark matter as a main candidate. But the problem is with the production in accelerator is in part of how heavy is the dark matter itself, like a particle, but also the type of interaction that is produced. Even though in this case of the minimal dark matter is electroweak processes, more produced via Z boson or Higgs boson. So there are the other complications that other type of interaction are much more stronger and more abundant the other type of particle that the accelerator can produce.
Okay, thank you.
Thanks, Roberto. Thanks.
Okay, thank you.
One announcement. Tomorrow morning, the first talk has been canceled. So the talks before the lunch will be moved 50 minutes early. This will start at 8:50. Sorry.